Everyone, can you hear me?
Yes, we can hear you.
Oh, great. Welcome to the 5th Bridging Transportation Researchers Conference. Hi, my name is Jinping Guan. Welcome to the Eastern Section, Track 1, Day 1. I will be the section chair. Right now, let me introduce myself first. I'm a associate professor at the Harbin Institute of Technology. And previously, I worked in the Massachusetts Institute of Technology. Welcome to join us today. So we have 5 presentations in total. So since we have the, as you can see on the screen, we'll have the headline presentation right after the section today and in the exact same room. So dear presenters, please kindly make sure to keep the presentation and the Q&A within 23 minutes. And with that, I will hand it over to our moderator. Yeah.
Hi, thanks, Jim. So I'm Irannezhad. I'm from the University of Queensland, and I'm currently a third-year PhD student. And so without much ado, so we can, I think, move on to the first presentation of the session 1 of the Eastern Day program of the day 1. And unfortunately, the first presentation, the presenter is not available in person to deliver the presentation. So I will share my screen and play the video. Yeah, so the topic is about end-to-end transformer for explainable autonomous driving. Can you see my screen?
Yes.
Okay, I'll play the video. Give me a sec. I think the video is not, you can't hear the sound of the videos, right? Okay, give me a moment. Okay. Let me try again. Sorry about that.
Hello, everyone. My name is Jiqian Frank Dong, and I'm a...
Can you guys hear now? Okay.
4th-year PhD student at Purdue University and also a researcher at Center for Connected and Automated Transportation. I'm sorry I cannot present this in person because it's fairly late at my place, and we are having an autonomous racing tomorrow, so I need to prepare for that. I'm sorry for that in advance, and if you have any questions, please contact me freely, and I will give my contact information at the end of this presentation. Okay, so my presentation is titled End-to-End Transformer for Explainable Autonomous Driving. So let's start with the background. So the vehicle automation is straightforward, is autonomous vehicles. There are a lot of the benefits or the anticipated benefits we are not realized yet. So to begin with, we have the mobility increase. For example, the road capacity, the parking availabilities can be all increased because of the vehicle automation, right? It's pretty straightforward, the distance between the two vehicles, the gaps that can be reduced, that increase the road capacity, and the vehicles can just rolling around without finding a parking during it can kind of run on its own without parking. And so the parking availabilities can be increased. Also the efficiency, it's anticipated to have no congestions, the safety to basically eliminate the human error, which is the 94% of the accidents. And also enhance the sustainability by reducing the emission and the fuel consumption. And above all, which is my favorite, we have more free time during commuting. And there's a very interesting the survey from Intel. It said there will be a reduction of to 50 million hours of users commuting time per year, and it can save more than 500,000 lives from 2035 to 2045. And it is only limited in US. Imagine if you kind of multiply it by a worldwide scale, then the benefit is enormous. However, this problem is we haven't achieved yet, right? A big question or the big problem for the autonomous vehicle is that do you actually trust in them? I'm pretty sure majority of us we don't trust them, right? Even if Tesla has a report that is actually the Nietzsche report from the US government saying the autopilot function for the Tesla vehicle only can reduce 40% of the crash. So that is from the statistics. So the autonomous vehicles are actually pretty safe, right? It's actually enhances the safety. However, the user trust is still a very big issue. And from another survey in 2018, and the results indicates 75% of the people, they are not comfortable with disconnecting vehicle equipment. That means when you remove the steering wheels, remove the pedals, 75% of the people will argue against that. And 64% of the people even show severe concerns on sharing the same road with the AVs. So basically, they don't even want to share the same road with AVs, let alone they were driving that, right? So why is people so kind of conservative? That's the kind of the research motivation behind this project. We want to enhance the people's use trust in the autonomous vehicles by making the autonomous vehicles more trustworthy. And very interestingly, more recently, we had the terms for autonomous driving is even banned in California. So basically, Tesla is not able to call themselves the fully autonomous driving vehicles anymore. And as autonomous vehicle researchers, well, this is my face. I'm pretty sad about that because we are even banned from the terminology perspective. So the research motivation of this project is that how can we regain the people's trust by making the autonomous driving vehicles more trustworthy. So the motivation behind it is that we can build actually the explainable AI for autonomous vehicles. So why the AI is generally not trustworthy is that they are majority driven by the black box computation, for example, the neural networks and other the deep neural networks and the models. So basically for those models, how the AI makes the decisions, we generally do not know the rationales. And as a consequence, we will never know when the AI will fail. So the failure is kind of unpredictable. And also we don't have a clue of how to improve the existing AI model. So we don't know how to kind of make it better in a systematic way. So the situation is even worsened by using the deep neural networks, deep learning, because those models are generally considered as black box. So it is like you only have the input and you get the output. You don't really know what is going on inside this model. So basically, the explainable AI comes as a rescue. So what does explainable AI do is that it gives you some like the intermediate result, lets you to probe what is this black box is doing. So basically, you can understand the rationale between the input and output for this AI model. So for this project, we are kind of narrowing down to build explainable deep learning models, especially for the autonomous driving context. So for the existing research, so you may argue that like we have those kind of predictions in the perception module. For example, you can detect all the vehicles on the road with all the the bounding box and even with a confidence level for the AI models. You think, okay, it's pretty explainable, right? So we have a the perception module itself is very explainable. Yeah, you can directly understand, okay, what the model is detecting. And if it's not detected in the correct way, and you can quickly kind of take it over. However, but these detections are not associated with your the decision, right? You detect a lot of vehicles inside this image, in this driving scheme, right? You can have the cars very far away. For example, this car, it's actually not helping you with the final the driving decisions, right? So what we are trying to achieve is to push this kind of explainable AI to a the decision level. Okay, so I want to not only give me the the detection results, those are explainable, but also make the entire the decision system or the goal intended system explainable. So we can argue that the single module cannot guarantee the system explainability, because that even if you have all these detections, they are explainable. Which detections are more important for your decision? You don't really know, right? You just fill in through it to another module and then generate the decision, right? Also, kind of if you present all this to the human driver, the people can get very overwhelming, right? You cannot actually kind of respond quickly when you face this high dimensional and high level features. So what we are going to build is to build an end-to-end explainable system that can jointly learn the driving decisions as well as the explanations behind that. So basically, it predicts the X driver's actions and also the explanation behind that. The logic is simply shown as this figure. Okay, this car said, okay, stop because the waiting for the pedestrians crossing. That's what we want to achieve. So we want a goal-induced system, so can learn from a end-to-end perspective. So we force the model to learn the rationale for those decisions. And to improve the explainability, we kind of built a learning paradigm of making the traditional decision-making task as a hierarchical task. So we first generate the language or the description of the driving environment. For example, here is the pedestrian is crossing or something like that. And then from this generated sentence, the textual sentence, we generate the driving decisions. So this part can be so simply by some rule-based approaches. So if you have the correct description of the driving scenarios, then the driving decisions can be simply achieved using some rule books. Okay, so we kind of shift the paradigm from the scenario to decisions. We add a description inside of it and then change it into a language generation task. Okay, so with the methodology part, we are building a fully transformer-based approach. So what we are trying to do is that, okay, we give you a driving, the driver's perspective, like the image of the driving scenario, and then you predict the language description of this. So it's more like a image captioning. So we need some like sort of image processing neural networks, so we can test with the traditional convolutional neural networks or the vision transformers. So basically the VIT, so which leverage the self-attention layer. So I don't want to go into the details about all these models details, but I want to mention, okay, why we want to use the vision transformer instead of the traditional CNN. Is that because for the CNN, it only has a short range correlation. It can only capture the nearby information. It's not globally kind of applicable. So if you want to achieve like a global visualization, you have to stack a lot of convolutional networks so that the explainability is even damaged. And also those kind of the convolutional neural networks, they are good at only the object detection, right? They are rotation, like the translation invariant. They're good at detecting objects. However, they are not good at detecting like the non-object regions. For example, the drivable areas. Those are like the background. It's just a part of the road. They are not labeled with any of the objects. So the traditional CNN would struggle with those cases. However, the vision transformer, it has a long range correlation. It can correlate each pixel with the rest of the other pixels of the entire image, and it has a larger perception field, and it's not specifically designed for detecting objects, right, from the mechanical ways. So basically, that kind of gives us the flexibility to detect, okay, the drivable area, the part of the empty locations that my car can move to. Yeah, so we kind of believe that the self-attention layer, the VIT, which is more suitable for the driving task. However, the VIT is very, very expensive in computation. So it goes quadratically with the image resolution, so which is very bad because we want this to be computed in real time. And also it has a fixed scale code token, so you cannot recognize like the variable scale objects. So some of the objects, they are closer by, they could be really big, and some of them are very far away, so they could be small. So we have to kind of adjust the transformer to make these kind of adjustments. Okay, so what the solution is that we leverage a newly developed transformer called the swing transformer. It kind of leverage the similar concept of the feature pyramid network. So it kind of zoom in from the small scale to the large scale, so you can have the multi-resolution feature, and at the same time it restricts the attention, like the inside all these windows. So basically, it's reduce the computation by restrict your attention. Right? So it's much cheaper in computation. So the key idea for this is that this swing transformer can leverage a hierarchical feature map and also in a shifted window attention mechanism, so that can reduce the computation cost and at the same time acquire multi-resolution features. And this is our the full architecture of our model. So we use the swing transformer here in the right to be our encoder, and we use a classic transformer for the decoder. So basically, the decoder generates the language, and the encoder kind of encodes the image so into the higher level embedding space. So we conduct a cross attention between the image features and the language feature, so that we can achieve a kind of language-induced visual attention. So this is actually imitating the human drivers, right? Human learning process, especially. For example, when you go to the driver's school, like for learning how to drive, so the coach will generally tell you, okay, where you should look directly. So for example, look into your left, and then there is something over there, and he will kind of guide your attention using a language. So this kind of mechanism can be imitated using this design structure called the language-induced visual attention. So it's achieved a cross attention here between the language and the image. So basically, it used the language captioning to kind of induce the attention of the vision. So during the testing time, basically there is no language. The model should be able to learn this kind of automatic attention from the driver scheme. So that can be achieved through this kind of framework. So it's kind of imitates the human drivers. Okay, so with those, let me introduce the experiment settings, which contains the dataset we're trying to use and all the other baseline models and stuff. So for the dataset, we are building our model and training our model on top of the BDD Berkeley Deep Drive OIA dataset, which is proposed in this paper in CVPR. And what it does is that it has the label for each of the actions and also the explanation. For example, you can move forward. The reason is that the traffic light is green, you follow the traffic, the road is clear, something like that. You have a language description of the driver's, like the driving decisions. The explanations of the driving decisions. Okay, so with that, I'm going to introduce the baseline models we're compared with. So if you think about that, this problem is kind of reduced to an image captioning model. So it generates the caption for each of the image of the driving scheme. So we are kind of comparing it with a traditional, like the classic image captioning model, which use the CNN, which is the convolutional neural network to encode the image, and then use like a LSTM or the recurrent neural network structure to decode the language, and also they can perform a attention inside of it. So basically, it's to kind of capture the correlation between the image and the language. Still have this kind of the like the cross attention between the language feature and the image feature. However, like the results shows that our proposed model, which is this fully transformer model, which performs much better than the rest of the other baselines. So that's how you get every single paper published, right? So in terms of like the reason generation, so it's a language generation task. So we have to generate the kind of valid language, right? You cannot generate some human not understandable language. You have to generate valid language. So this valid language can be evaluated through this blue score. So basically, it's to measure how good the language generation is. That a valid sentence? Is that a lawful sentence? Also something like that. And also we kind of map it to the reasons and also the actions, driver's actions. So to see, okay, this can be used as like the evaluation metric to kind of to tell people, okay, our model is good enough to generate the reasons at the same time generate the actions. So we beat all the baselines in terms of the language generation and the reason prediction. And also we are not adding a lot of computation cost, because here, like compared to some traditional models, we only add like 1 million parameters, still kind of makes much better performance. So for the results, you can see here from the qualitative result, you can directly generate the language here. So for example, this image here, you can generate the language of no lane on the left, obstacles on the right. So the SOS means the start of sentence, and EOS end of sentence. They are just the customized tokens for generating language. And the predicted action could be the cannot turn left and the cannot turn right, right? So it's pretty straightforward. So it match the ground truth labels. And also in this one, we also have the similar results. The obstacles on the right lane, solid line on the right lane, right? The solid line is here. The obstacles like the vehicle. So the action is that you cannot turn right. And the ground truth also matches like the solid line on the left, and then cannot turn left. But in this image, I think our model is actually better than the ground truth, because actually from this image directly, we can still like merge to the left. Also, because of this is a fully attention-based method, we can kind of visualize the attention map, which gives us better kind of explainability. So you can see here, we can directly predict the solid line here, right? By generating these words, right? It's actually the model actually looks at this brighter place. So also for this right, it also look into the correct locations. So this kind of gives us a explanation of whether our model has looked into the correct locations by visualizing these attentions. Yeah, so we can have a better explainability. Also for this one, we can kind of have the similar result, the solid line on the left. Yeah, and also there's no line on the right, right? The right is completely no line. Okay, so for the summary, we have trained an end-to-end explainable model for both perception and planning. So you can directly generate the descriptions and then the actions, right? So we achieve higher interpretability in terms of the rationale of the decisions can be evaluated, and we kind of get the better interpretability by visualizing the attention map. You can directly probe, okay, whether my model has learned the correct rationale and also look into the right locations. And it has better model performance because it outperforms all the baselines we have. So what are the applications of our model? So basically, our model can be directly deployed to those level 3 and above autonomous systems, which can help you to quickly eliminate the irrational decisions. Okay, if the like the autonomous driving vehicle is making some irrational or like the stupid decisions, it can quickly tell you, okay, those decisions are not valid, and then eliminates them. So basically, it can perform as a safety node and also a callback node to kind of enhance the overall safety of the autonomous driving system. Okay, I'll leave my contact information here in case you have any questions or you have any suggestions. Please feel free to contact me directly. And I'm sorry again, I cannot present this in person because we have other duties to perform in the early tomorrow. And I really thank you for your attention. Thank you.
All right, thank you. And so I will move on to our third speaker since I haven't seen the second speaker join us. So Shuo, can you hear me?
Yeah, I can hear you.
I will hand it over to you, and feel free to share your screen, and thank you.
Thank you. Okay, so like share my screen. Okay. Okay, can you see my slide?
Yes, we can. Yeah.
Okay. Thank you. Okay. Hello, everyone. This is Shuo Feng. I'm an assistant professor at Department of Automation at Tsinghua University. So today, I'm very happy to have the opportunity to talk about our recent work on the AVA safety validation. So the title today is Dense Reinforcement Learning for Safety Validation of Autonomous Vehicles. Today I will mainly introduce you the major ideas of our this work, and you can find more details of this work published in Nature early this year. So okay, all right. So autonomous vehicles have attracted significant attention during the recent years because of their great potential for revolutionizing traffic safety, mobility, and sustainability. By 2016, there are several AV companies have announced that they would mass producing high automated driving systems before 2020. However, those expectations have not achieved. Right? Today is 2023, and so far there is no highly automated driving system available in commercial. And even some news say that a long cold winter is here for self-driving cars. There are multiple reasons for this bottleneck, and above all, we think that the safety issue is a major challenge for the AV to be largely deployed in on public roads. Let me show you some examples. For human drivers, we have on average one accident every 1 million driving miles in the United States, and we would like to the AVs to be safer than the human driver on public road. although we don't know the exact number of the AV regarding the crash rate, but we can indicate from the other statistics such as the disengagement rate that so far the safety performance of AV is still below that of human drivers. There are two major reasons, two major challenges for the safety issue of the AVs. One is the well-known curse of dimensionality. The reason is that the safety performance of AV, the key of safety performance of AV is to interact with the human-driven vehicles or vulnerable road users. So since the behaviors of those vulnerable road users and human-driven vehicles are significantly affected by different weather conditions, road infrastructure, different road users and maneuvers, the AVs need to handle all such different cases in public road. So the dimensionality of the AVs need to handle is very high. Another one is what we call curse of rarity. The basic idea is that the occurrence probability for the event of interest, such as crash events or safety critical events, is so rare on public road, so that most available data contain little information regarding the safety critical events. So that if we want to evaluate such a rare safety critical event or optimize regarding such a rare safety critical event, we would face significant new challenges besides the curse of dimensionality. In summary, for AVs, we think that the existence of both curse of rarity and curse of dimensionality are the root causes of various safety challenges in the development and deployment of AVs. So such challenges exist in different stages of the AVs and different components of the AVs, including the perception, decision, prediction, control, and also the validation. And since the current deep learning algorithms cannot well handle such types of challenges, so the AVs face severe safety challenges. So that's our thinking on the safety challenges of AVs. And today I want to elaborate on those challenges and our preliminary solutions regarding on the task of AV testing. So the AV testing, the goal of AV testing, including the two major parts. One is how to identify the long tail of events for the AV, so that we can further develop and improve the AV safety performance regarding those long tail of events. Another one is given an AV, how to systematically evaluate the overall safety performance. For example, we would like to know the correct accident rate of the AV if largely deployed on public roads. However, according to the NASA status data in 2019, there are about 1 death per 100 million miles for human drivers. So to prove AVs are 20% better than human drivers using a fleet of 100 AVs driving, we would need to drive the AV around maybe up to 5 billion miles on public road, which would take around more than 200 years. So this way is intolerable inefficient for the AV to testing an AV. To address this inefficiency issue, we proposed what we call the AI against AI methodology. So the first AI denotes the testing environment. We would like to develop what we call an intelligent testing environment, ITE, to test the AV. The second AI is the agent, the AI and the test. Here in this case is the AV and the test, right? So the basic idea is that we want to develop an intelligent testing environment to interact with the AV and the test, so to achieve our testing purpose, testing goals. So that's the basic idea. So to be more specific, for the AV and the test, as shown in the left-hand figure, the white vehicle, we would like to train the behaviors of all the surrounding traffic participants. For example, here denoted by the green vehicles, all those green vehicles, the maneuvers will be controlled by our neural network. So which can result in the what we call the ITE, the intelligent testing environment. Through the interaction between the ITE with the AV and the test, we want to achieve the two major goals. One is we want to evaluate or predict the safety statistics of the AV if largely deployed on public road, such as the crash rate, injury rate, of fatality rate for the AV and the test. Here we call the ITE is unbiased. Another goal is that we want to utilize as small testing miles as possible to evaluate such safety performance of the AV. So in other words, we want to achieve the efficient testing of the ITE for AV. So that's the two major goals, and regarding the generation of ITE. To achieve these goals, we developed a framework including two major components. One is what we call the NDE modeling. Another one is ITE modeling. The NDE modeling, the idea is our NDE modeling is to utilize large-scale natural listening driving data of human-driven vehicles of one of our road users to reproduce the real-world traffic environment. So the goal of the NDE is to ensure the unbiasedness and accuracy of the testing of AV testing in the NDE. And then based upon the NDE modeling, we would further generate the ITE, which is to accelerate the AV testing by learning sparse adversarial adjustments to the NDE. So I will introduce the major ideas one by one. The first one is how we model the NDE. There are multiple. There are some existing studies regarding the NDE modeling. But several limitations exist. The most widely applied, the most applied way in industry regarding NDE is to directly utilizing the replayed log data. The key idea is that we utilize some data collecting vehicle to collect the surrounding trajectories of the trajectory of surrounding background vehicles, and then replay those log data into our simulation platform to test the AV. However, those trajectories are fixed trajectory and cannot interact with the AV and the test. So such testing is not accurate, and it could introduce severe biasness. The second one is to utilize some traditional driving model developed in the transportation domain, such as the car fogging model, lane changing model. Those are widely applied in traffic simulators such as Sumo and VSIM. However, those models were usually developed for the traffic efficiency purpose, not for the traffic safety. So they are usually oversimplified based on heuristic rules and cannot be used for the AV safety performance testing. The last one is to utilize some prediction model developed in AV domain. However, such prediction model are usually short-term prediction model and cannot be utilized for long-term simulation testing. To address those limitations, we developed what we call neural NDE, which is a pure data-driven modeling framework to leverage the large-scale natural listening driving data and also the advanced of the AI technology. For example, we utilize the transformer architecture as well as a safety mapping network to train the neural network to which can simulate the background vehicle maneuvers in the simulation. So here, let me show you some examples. We equipped several infrastructure-based sensors, such as the cameras, to contact, track, and track the trajectory of all the background vehicles in a roundabout. And then, as shown in the right-hand figure, we can replay those log trajectory in our simulation platform. Based upon those large-scale log data, we train our neural network, the neural NDE, and then we can utilize neural NDE as an NDE model to simulate to test AV in the simulation. So here I want to compare our neural NDE model with the real world regarding the safety critical events. The left-hand video shows the real crash collected in the roundabout through the infrastructure-based videos, the cameras, and the right one shows the simulation result using our neural NDE. So you can see that in the neural NDE we can simulate some realistic crashes for the AV compared to the human driver crashes shown in the left hand. So here you can see that these two vehicles have a side collision, and as shown in the right hand, you can see that the pink vehicle had a side collision with the blue one. And besides of the case study, we also evaluate the performance of the neural NDE model regarding the distribution of safety statistics, such as the vehicle speed, distance, yielding speed, things like that. So here the blue line denotes the distribution of the ground truth, and the green line denotes the distribution of the model in Sumo, which has been calibrated utilizing the ground truth data. And the orange one denotes the result of the neural NDE. So you can see the Sumo data, the Sumo simulation, although after the calibration can have a good mean value, but regarding the distribution, the accuracy is not that good. While our model can have a better distribution performance. So regarding to the AV safety performance testing, we more interested in the distribution accuracy, particularly for the long tail distribution accuracy, because those long tail distribution will influence the safety performance significantly. And we also look into the details of the safety critical events, such as the different crash type, different crash severity, and also the near miss statistic. We can see that our approach, the neural NDE, can better reproduce the distributional accuracy regarding to the safety critical events compared to the ground truth. Okay, so the next part is how we further generate ITE based upon the NDE model to further accelerate the testing process. The basic idea is that we want to formulate we formulate the behavior of the surrounding background vehicle as a reinforcement learning problem. So as shown in the left top figure, the blue vehicle denotes the AV under test, and all the green vehicle denotes the surrounding background vehicles. So the surrounding background vehicles have been controlled by the NDE model developed by the neural NDE, right? Right now, we want to further add on a reinforcement learning neural network, trained neural network to further adjust the behaviors of the surrounding background vehicle. So we will not go to the details of the formulation of the reinforcement learning, and you can find more detail in our publication. So after formulation of our reinforcement learning, we found that existing reinforcement learning techniques cannot address such a problem, because most existing IL techniques focus on how to address the high-dimensional problems, such as the goal and the chip design. The goal is the state space of goal is more than 10 to the power of 300, and the chip design is more than 10 to the power of 3,000. However, as we discussed at the beginning, autonomous vehicles not only suffer from the high dimensionality, but also suffer from the curse of rarity. So existing reinforcement learning techniques cannot address the curse of rarity and the curse of dimensionality simultaneously. We developed what we call the dense deep reinforcement learning to address this issue. So the basic idea is that we want to add the Markov chain and then utilizing the added Markov process to train the neural network. So the basic idea is that after collecting the data in the simulation, we will add the data and densify data and only utilize the data that are critical for the AV for the safety to train the neural network. So through such a way, we can equivalently add the Markov process and achieve the dense deep reinforcement learning approach. So here, let me show you some results. We utilize the open source data in the rounding. And the left-hand figure denotes the log data collected in the real world, and the right-hand figure shows the simulated data in our utilizing our neural NDE model. So you can see that as shown in the left-hand figure, the human driving behavior are very stochastic in the roundabout and highly interactive. So as shown in the right-hand video, our model can well reproduce such interaction and uncertainty in the simulation. So so then we can replace one vehicle as the AV and the test in such simulation platform, and then we can test the AV through the neural NDE model. Okay. So then we here the red vehicle has been replaced by the AV and the test, and all the surrounding background vehicles are further controlled by the reinforcement learning trained neural network. So you can see that based upon the neural NDE model, the reinforcement learning can further accelerate for further improve the probability of the adversarial maneuvers of surrounding background vehicle, so that the crash rate of the AV in the test will be increased. And through the impulse sampling theory, we can weighted each crash in such a testing environment, and then achieve the unbiased estimation of the safety performance of AV regarding different safety, different crash rate, crash severity, and different safety critical events distribution. So as shown in the right-hand figure, we can evaluate the crash rate, crash severity, crash type, things like that of the AV. So here are the major results regarding crash rate. So the blue line denotes the evaluation result in the NDE model, and the red line denotes the evaluation result in the ITE model, which are trained utilizing the D2IL approach. So you can see both methods can achieve the same accurate estimation regarding the crash rate, which means that our approach is unbiased. And to achieve the same accurate result, our approach we are only utilizing much smaller testing number of tests, which means that our approach is more efficient. So here, for this specific case study, our approach can accelerate more than 2,000 times faster compared to the testing in the natural environment. And besides of the simulation testing, we also test the real AV in the real world utilizing our ND and ITE model. So we equipped an MKZ vehicle with the open source driving automated driving system, Oliveira, and we test the AV in two test track. One is MCT test track, another one is the American Center for Mobility test tracks. And here is the results. So to test the real AV in the real world with our generated ITE, we developed what we call augmented reality testing platform. So the key idea is that we want to utilize the simulated virtual background vehicles to interact with the real AV in the real world in real time. So through, as shown in the right top video, you can see this is the front camera video of the AV. You can see during the testing, the AV has no surrounding background vehicles. However, as shown in the right bottom video, you can see that all the surrounding background vehicles will be augmented in the AV perception domain space. So through this way, the real AV can interact with the virtual background vehicles, and the behavior of the virtual background vehicles was controlled by our development of the neural NDE and ITE as discussed before. So through this way, we can test the AV, the performance of AV in the real world. Okay, so you can due to the time limitation, I didn't introduce too much details regarding the method. So, but you can find out all the details and the videos in our publications. All right, that's all from my side. Thank you.
Thank you, Shuo. I think we have a question in the chat box from Kara, and we will have a quick Q&A section. Yeah, please take a look at the question. Yeah.
Okay, yeah. So greeting from everyone. Fish eye camera view. Yeah. Data also. I'm not sure they use data for yeah, being used. Oh, so the first question is how to utilize fisheye camera for license plate reading. Yeah. So that's a good question. Actually, I don't know. I also don't know because the fisheye camera has some several limitations because as you can see that the plate cannot be well. I think the plate cannot be well identified through the fisheye camera. So in this study we utilizing multiple fisheye camera to focus different regions in the roundabout. So through such way, and then we calibrate all the camera because the camera are fixed on the infrastructure based equipment, so we can well calibrate those cameras and then to transform those video into a bird eye view. So through this way, we can identify and detect the vehicle in the roundabout. But I don't think the quality of the video can be well used for the license reading. I don't know. Yeah, so that's the first question, I think. The second one is data limitation reason why. So I think the third question is why we're utilizing a roundabout as case study, which to be safer than other kind of interaction. So one reason is that the roundabout is not safer than intersections. So actually, the roundabout we utilize is one of the top 10 dangerous interactions in Michigan. So that's the one reason why we utilize that roundabout. So as you see that in the roundabout, actually the interaction is more complex because there is no signal and no stop sign. So the interaction usually is more complex, which may be counterintuitive, but that roundabout is more dangerous than most interactions in Michigan State. Okay, I think yeah. Okay.
Any other questions, comments about Shuo's presentation? Okay, and if not, oh, we're right on time. Great. If not, oh, we have one more.
Oh yeah.
Yes, go ahead.
Figures in figure page 20. Y relative gap. Yeah, let me find this. 27. Oh, Y relative gap in ODE is larger. So can you? Sorry, I don't know which. Page 23. Okay. You mean this one? Okay. Y relative gap in NDE is larger. Yeah. So that's because the NDE, the testing in NDE is inefficient than the testing in ITE because although the NDE in testing in NDE we have more number of tests, but the occurrence of safety critical events is less than the ITE. For example, if the crash rate is 10 to the power of -6, so when we testing in NDE, every 1 million driving miles, we would encounter one crash. So if you only testing 1 driving miles, then you may experience 1 crash, or 0 crash, or 2 crash in this test, right? Right? Because this is stochastic. But when you estimate the crash rate, you will obtain the crash rate is 0, or the 10 to the power of -6, or 2 times 10 to the power of -6, or 3 times 10 to the power of -6, things like that. So the uncertainty and the biasness of the evasion, so the uncertainty of the estimation is very large. So that's the reason why the relative half width in NDE is even larger, although the testing number is large. Although more number of testing has been conducted. Okay. Is there any new other question?
Any other questions, thoughts, and comments? And if typing is not fast enough, feel free to raise your hand, then we can talk about, like, we can have like conversations too. Yeah. Okay, so if there's no more thoughts and comments, then we will move on to our next speaker. Thank you, Shuo. Thank you very much for the great.
Thank you. Thank you, Professor Guan. Thank you.
So we'll move on to our next speaker, Riki. Riki, can you hear me?
Can you hear my voice?
Yes, great. And feel free to share your screen.
Hey. Can you see my screen?
Yes, we can see it. And it's not in the full screen mode. Now it works. Yes.
Okay. Okay, thank you. And thank you for Dr. Juan. I am honored to be here and to be here today online and talk about my recent research. So my name is Riki Kawase, assistant professor at the Tokyo Tech in Japan. Today, I'm going to talk about my recent work on stochastic system optimal assignment for ride sharing system. And especially the challenge was to characterize the theoretical properties of the control in dynamic system optimum and DSO assignment. And we know ride-sharing systems are expected to be a north-wide solution to mitigate traffic congestion by allowing drivers with similar itineraries and passengers to share surplus vehicle seats. In addition to social benefit, and ride-sharing drivers can qualify to use HOV lane for quick trip, whereas passengers can option a flexible and faster travel mode as the alternate public transit. And the dynamic assignment of drivers to passengers plays a central role in the successful of ride-sharing and further advance in communication technologies such as mobile phone and the GPS enables ride-sharing platforms to receive trip information from passengers and drivers and then match them real time. And furthermore, utilize real-time information on traffic states can lead to minimize not only traffic congestion in the HOV lanes, but also the general lanes, resulting in minimizing whole network costs, and dynamic system optimal DSO. And recently, various powerful decision-making tools have been developed to address the dynamic assignment for vehicles to passengers, and they are classified into individual-based model and flow-based model. The former usually assumes the load networks with exogenous travel time or virtual point-to-point network formulated respectively as VRP, vehicle problems with pickup delivery or the matching problems. However, the existing previous studies on individual model have mainly focused on scenario where the number of vehicles is smaller. And that is like showing some do not significantly affect traffic congestion. Although several studies related VRP problems include endogenous congestion, but they describe only flow congestion, which is inappropriate for dealing with the peak congestion. The latter flow-based model aims to capture sophisticated traffic congestion by describing individual vehicle and passenger and continuous variables. And this study focuses on flow-based model as a decision-making tool that contributes to solve traffic congestion. And there are two major streams for flow-based dynamic vehicle passenger assignment and discrete time model and continuous time models. The first solves discrete time disassignment problems in general networks as linear optimization problem by employing the classical list of problem techniques of linear relation and the reduction of congestion flow propagation. Since Levin have developed linear programming for congestion-aware vehicle routing and passenger matching, and this stream has incorporated pickup drop-off time window constraints and integrate with public transit and infrastructure design. The second stream examines exact solution to continuous time DS assignment problems in simple network, mainly parallel link network consisting HOV lane and the general purpose links. They can provide a theoretical underpins for efficient numerical algorithms as well as analytical insights. It is worth noting that parallel networks are very common when studying the morning commit problem, although the analytical method may not be extendable to general networks. Although the numerical powerful tool for this assignment for ride sharing has been developed, they face significant limitation in lacking consideration and stochastic assignment, stochastic in traffic states. That if the dynamic of traffic state would be deterministic, model output and observation are consistent, unfortunately, in traffic state as stochastic due to uncertain traffic demand and traffic behavior and other factors, especially during peak condition. The real-time information observation and prediction of uncertain traffic state has mitigated the negative impact. However, dynamic vehicle passenger assignment discarding future risks in previous studies may miss more effective solution. Therefore, it is significant to consider stochastic traffic state in dynamic ride sharing. Now, lastly, identify the properties of the DSO assignment for ride sharing with stochastic travel time in parallel networks. We focus on the continuous time DSO assignment problem in network with 3 parallel links. The first, HOV link with a single bottleneck. The second represents GP link that can be considered an aggregate of the road networks. And the third is a public transit for non-ride sharing passengers. The outcomes of this study are as follows. And for theoretical outcome, we reveal that the DSO assignment consists 25 patterns as a combination of 5 vehicle inflow controls and 5 passenger inflow controls. And the optimal control is monotonical with respect to queues for ride sharing service and travel time for other travel modes. Furthermore, the above 2 properties allow the optimal conditions can be stated as equivalent dynamical system of GCP and generalized complementary problems. This reformulation provides us with efficient and lowest algorithms for obtaining quantitative results for the problem, but due to time limitation, today's presentation explains above the 2 properties. And for numerical outcomes, our numerical explained provides the sensitivity of the optimal control to risk calibration and variability, and the option value of the feedback control comparing the operative control bar. Okay, now I will move on the model section. This slide shows a schematic figure of the parallel link network considered in this study. And this study focuses on parallel link network like this, with single bottleneck connecting a single OD pair. And this network compares 3 types of links, HOV links for ride sharing, and ride sharing vehicles and passengers, and the general purpose link for non-ride sharing vehicles, and the public transit link for non-ride sharing passengers. Sorry. So we assume that arrival rates, the origin for vehicles, and the large S, and the passenger large Q are known, and the platform operators can assign small s vehicles and small q passenger to the HOV link. Then the remaining supply and demand are assigned to the public transportation link and the general purpose link respectively. Now we make the following conflicting the assumption for the HOV link and other links. And specifically, we assume that the capacity for the HOV link is small enough to cause bottleneck congestion X and I, whereas that for the other links sufficiently large comparing to the vehicle supply large S and large Q. And moreover, the free flow travel time or HOV link is normalized to 0, and we evaluate the relative travel times for other links CS and C2. Okay, in the problem setting, we formulate the system dynamics and network dynamics as follows. On the HOP links, there are big Q and big QI and percentage QX. The evolution of the Qs is governed by inflow and outflow rates. And this C models link flow dynamics with Poincare model. Then the evaluation of the Qs is formulated as follows. And the inflow rates and small s and small q are control variables, and outflow rate kappa on the kappa depends on the state of qx, x, and qi. Specifically, when bigger passenger q exists, the outflow rate is equal to the bottleneck capacity kappa, and otherwise, the assigned vehicles or passenger flows to the HOP link past or face the bottleneck. And this slide shows the travel time for the GP links and public transit links. The CS and C2 are supposed to evolve unpredictably due to many factors such as traffic accident and timetable disruption and so on. And when we express the stochastic dynamics of CS and C2, the geometric Brown motion, which ensures that to be non-negative, sorry. And Z standard deviation processes, and mu and sigma drift rates and the plurality parameters respectively, and the subscript indicates the corresponding links, and each first term, this one in E2 and E5, indicates the deterministic dynamics of the travel time, while the second term indicates stochastic dynamics, that is travel time uncertainties. And we assume a single platform operator should minimize social costs in the network during the planning horizon with the above system dynamics. And the simplest expression of social cost is expected total travel time as follows. But unfortunately, this expression allows for risky assignment strategy, where the worst case F is very, very large, that is, variance F is large despite a small expression, and therefore we need to consider trade-off between risk and return in controlling the stochastic social cost. To model this trade-off, we assume the social cost is evaluated through the risk-averse function. As you can see in this figure, this function can lead to a risk-averse strategy by measuring a higher cost for the worst case. And therefore, the DSO assignment problem for ride sharing can be formulated as the following stochastic optimal control problem. And the linearity and the convexity of this problem provides us these good mathematical properties. First, and differential equation describes system network dynamics, and control constraints are linear with respect to control and state variables. This linearity ensures the SOCP, space optimal control problem, satisfies the constraint qualification. Therefore, this stochastic maximal principle the Feng 1919 and in the method condition. And second, the integrated is convex, and the differential equation are linear with respect to variables. These properties ensure that SOCP satisfies a Mangasarian sufficient condition, which is the second optimality condition of stochastic optimal control problem. And accordingly, the stochastic maximal principle can is the only global optimal to SOCP. It's very good mathematical properties. And next, I will explain theoretical result. And due to time constraint, this presentation provides only the proposition without the proof process. And first proposition is the DSO assignment patterns consists of upper bounds, lower bounds, and interior solution. And this assignment pattern is characterized by the relationship between the social marginal cost of the HLV link, this one, and that of another links, that's one. And where the V depicts the value function of SOCP. And next, second proposition shows the upper bound and lower bound solution. Specifically, the upper bound solution is S and 2 are independent of traffic state. On the other hand, the lower bound solution are classified depending traffic state X and I, so as to ensure non-negative constraint and set bias like this. And this is because when the optimal control is the lower bound solution, this one like this, and the SMC social marginal cost of GP is lower than that of HLV, and the flow should be assigned to GP link whenever possible. And whenever the passenger queue increases due to the absence of vehicles, the SMC social marginal cost of HLV link is smaller. In other words, the lower bound solution attempts to reduce the counterpart queues without increasing its own queue. And the third proposition as follows: interior solution. An interior solution is had and you had as well, and given by like that. And the property of interior solution is the monotonically decrease with respect to queues X and I, whereas monotonically increases with respect to travel time, like this figure. As you can see in this figure, interior solution like this, that smooth bridges, and the upper bound solution and the lower bound solution. And this table and this table summarize the properties of the DSO assignment in proportion 1 to 3. As you can see in this table, the optimal control of vehicles consists 5 patterns: a single upper bound solution, a single interior solution, and 3 lower bound solutions, depending the traffic state, including the queue, vehicle queue and passenger queue, and the travel times, and the total supply and demand. And similarly, the optimal control of passenger also consists 5 passengers, a single upper bound, a single interior solution, and 3 lower bound solutions. Therefore, DSO assignment strategy for ride sharing consists 25 patterns as a combination of vehicle flow control, as a combination of 5 vehicle inflow controls and 5 passenger inflow controls. In order to examine the detailed properties of the control strategies, we conduct numerical experiments. And this slide shows parameter setting in our numerical experiment, and risk above function is defined as follows, where theta represents risk abateness. The larger it is, the larger risk abateness becomes. Okay, and this slide verifies the monotonicity of the optimal control. In the left figure, the horizontal axis shows the passenger queue X, and the vertical axis shows the vehicle queue. And the right figure, the horizontal axis shows vehicle queue, and the vertical axis shows travel time for GP link. And the curve shows the optimal control of vehicles. As you can see in this figure, interior solution like that, interior solution increases with respect to travel times, this one. And on the other hand, decrease with respect for the ride-sharing queues, this one and this one. And in the following slides, I will numerically verify how the upper bound and the lower bound changes. Specifically, blue line shows the upper boundary, and the red line shows the lower boundary. And this slide shows the upper bound and lower bound change over time. And the horizon axis shows the vertical QI, and the vertical axis shows the travel time for GP link. First, I will show only upper boundary. As you can see in this figure, the domain of the upper bound solution like this, and like this, like this, and like this, and expands over time. And in contrast, this figure shows only lower boundary, where the domain of the lower bound solution like this, and like this, and like this, and like this, and allows the over time. And furthermore, this figure provides the property of the interior solution that the domain of the interior solution between the upper boundary and lower boundary, this one, is close to 0 and over time. And this property implies employing a risk-free strategy, and that is assignment to the edge of a link, because significant losses cannot be recovered in a short period. And next, this slide reviews the sensitivity to the risk aversion. And similarly, the horizon axis shows the big QI, and the vertical axis shows the travel time for GP links. And as you can see in this figure, the smaller the risk aversion, the smaller region of the interior solution is close to 0. And furthermore, the changes become very sharper as the risk aversion decreases. From this result and this result and this result, we can conclude that introduction of risk aversion has the effect of smoothing the optimal control. Then next, this slide shows the sensitivity to the variability. In left figure, actually shows the passenger X and vertical Q, and then so on. And as you can see, when the variability there increases, and like that, and the domain of upper bound solution expands, and the domain of lower bound solution narrows. The reason for this is that the greater variability implies a higher chance of encountering a small value of travel time in the future, in which the platform operator can improve social costs by decreasing the queue length. Therefore, higher variability increases the optimal queue length and shift both boundary curves like that. In other words, the platform operator has an option to feedback management of the queue length, and the economical value of the option increases as travel time variability increases. And finally, this slide reveals the performance of the feedback control. And the horizontal axis shows the variability, and the vertical axis shows a value function, and that is control performance. The solid line shows the performance of feedback control, and dashed line shows the open loop control. As you can see in this video, feedback control is always efficient, especially as the variability increases, value function buoy decreases. This means that the greater the uncertainty in travel times like that, the more variable real-time observation information in feedback control dynamic traffic assignment. Okay, let me summarize my works. Now, recently, ride-sharing service gathers attention as a noteworthy solution to mitigate traffic congestion. Nowadays, to improve the dynamic assignment of vehicles to passengers, some digital assignment models have been developed. However, they discuss the stochastic elements. Despite inevitable uncertainties in traffic states, then this explores dynamic system optimal assignment for ride-sharing on a network with 3 parallel links in stochastic environments. We review the qualitative properties of the DSR assignment. For example, the DSR assignment consists 25 control patterns. And it should be noted that this study is designed as an initial step towards analyze the properties of the DSR assignment for a system. And our analysis may be expandable to a more complex model, for example, with departure time choice in a general network, in general parallel network, and with macroscopic fundamental diagrams, and with stochastic demand and supply, but this is done. this have done. And there are my reference in this presentation. Okay, that's all. Thank you so very much. That's all.
Thank you. Any thoughts, questions, comments?
Yes.
Let's wait for a couple minutes and make sure people are not typing, or if you have questions, feel free to raise your hands too. All right, any other thoughts, comments for Riki? Okay, I think we're good. All right, so next, let's welcome Ali. And Ali, can you hear me? Feel free to share your screen.
Hello, everyone. Hello, dear Dr. Xuan.
Hi.
Pleased to meet you.
Hi, Ali.
You.
Yeah, feel free to try to share your screen, and we're glad to have you join us today. Thank you very much.
Okay. I'm delighted to be back at the BTR conference with dear researcher and dear professor, Dr. Xuan and dear Dr. Kockelman, and all of the friends and researcher here. You have my voice?
Yes, yes, we can see the
It's okay.
screen. and
Yes.
we hear you.
I think the video is weak. The topic of my presentation is an interdisciplinary research between transportation and psychology. Drivers reported crash histories, sensitivity to reward and punishment, personality, and a demographic case study in Iran. First, I'll start with a brief overview of other academics' perspectives and the finding of their studies. Human behavior results from knowledge, skills, and motivation. Most road crashes are caused not by lack of knowledge or skill, but by lack of motivation to behave safely, and unsafe driver motives such as personality, cognitive abilities, for example, visual memory, sustained attention, stress trigger, anger, dominance, and etc. are often unconscious. And traffic psychology help to raise driver self-awareness. Everything which a person is aware of can be controlled by that person, and everything which a person is not aware of control the person. In driver training, we learn what decide in traffic, and from psychology, we can learn to understand how we decide. The main cause of road crashes are errors due to maladaptive behavior in interaction with roadway or other vehicle. It's better to divide a behavior sequence up into a single element and analyze the reward system in order to know what keeps the habit alive. For example, in Iran, in our society, this is especially true of people who drive too fast. The majority of people who have committed driving offenses that go behind minor misdemeanors, display relevant type of behavior that these underlying attitudes have developed over many years. Regarding our research variable, we have 9 latent or independent, or also we can call exogenous variables: introversion, extraversion, neuroticism, psychoticism, sensitivity to reward and sensitivity punishment, attitude towards safety, and driving behavior, and also one dependent or endogenous variable about reported crash history. What is the definition of this variable? These 3 diagrams show the meaning of this variable. Also, this figure shows the high and low score of each variable based on Ising personality theory, and for example, introversion versus extroversion, and stability versus neuroticism, and self-control versus psychoticism. The difference between E and I, extroversion and introversion, here we can talk about the difference between 2 types of personality. Extroverts rely more on dopamine. When information passes through their brains, it goes through a pathway called dopamine pathway. Also, the information received by introvert's brain travels through a much longer pathway called acetylcholine pathway. Since this path is so long, introverts tend to overthink more than extroverts do. For example, in driving, they react with more attention and patience. Also, introverts have better judgment and control. Some of the other of introverts and extroverts showed in this picture. Regarding to reinforcement sensitivity theory, RSD, there are 2 separate but interacting systems in the brain of mammals that control emotional behavior and are the basis of personality differences. A behavioral activation system, BAS, which represent sensitivity to reward cues, and BIS, behavioral inhibition system, which is responsible for sensitivity cues. About gray matter, the prefrontal cortex is the part of brain that regulates personality, decision-making, and social behavior, for example, driving behavior, among other things. It contains gray matter, which is a type of tissue in the brain where most of its activity happens. Introverts tend to have a larger, also thicker in their prefrontal cortex than extroverts. According to the Gray theory, people with high behavioral activation system, and according to the Ising theory, unstable extroverted person seeking stimuli and have more sensitivity to reward and show risky behavior. But according to RSD, people with high behavioral inhibition system, and according to the Ising, a stable introverted person avoiding stimuli and show sensitivity to punishment and behave in safe driving. According to the Lajunen finding, figure shows in their findings that number of traffic fatalities was high in countries scoring high in extroversion. Also, a moderate amount of neuroticism seemed to benefit traffic safety, whereas low and high score on the factor of neuroticism scale might increase the number of fatal road crashes. What is the purpose of our study? This study aims to generate a structural equation model of road crashes involvement in Iranian drivers to better understand latent cognitive and behavioral factors influencing their reported crash histories. It is hypothesized that personality trait, introversion, extroversion, neuroticism, psychoticism, sensitivity to reward and punishment system, driving behavior, safety attitude, experience all contributed to crash reported history. Regarding to method and data collection, participants' data remained anonymous and confidential throughout the research. The study used stratified random sampling and 4 regions and 6 main streets were selected from each region to distribute the questionnaire, and the random sampling was carried out with the consent of individual according to the population density and proportional allocation to each of the region. And the sampling lasts 1 month, and finally 425 valid questionnaires were selected for analysis. And the questionnaire were completed in semi-supervised self-administered manner with the consent of the driver. It took about 20 to 30 minutes for driver to answer all 4 questionnaires completely. And we use Ising personality questionnaire, Trobia, sensitivity to punishment and reward, Manchester driving behavior, and also Chen safety attitudes. One of the important variable in our paper was reported crash history. The 2 indicators were utilized to assess involvement of drivers in road traffic crashes, traffic violation index, and crash index. In first approach, according to the history of recorded traffic violation of each person, the corresponding statistic and information of the sample were collected using Iranian traffic police report. Also, in second approach, the information was obtained through report questionnaire. 2 questionnaires assessed the driver crash history, minor crash, and severe crash that they had in last 3 years. For example, for minor crash, that means resulting in limiting damage, PDO. And this implies that researchers asked drivers for permission to access their police traffic records. Unfortunately, participants gave permission for the researcher to access their crash and violation records. Also, a confounding factor is exposure, since drivers who drive greater distance each year will have more crashes and more violation, even if there is no link between violation and crashes. And using 2 above mentioned indicator and including a measure of exposure as covariate in the analysis, the involvement of drivers in road traffic crashes was determined. I should emphasize that if there was a lack of agreement between the 3 sources regarding what value was selected for the crash index for particular driver, a greater weight was put on police and insurance records, and self-reported information was also asked again for verification. In terms of descriptive statistic, most of the respondent persons were male and married within age range of less 30 years. Most respondents had a bachelor or master degree. A significant percentage of respondents had a job unrelated to driving, and their driving experience and driver license was about 5 to 10 years old. And in connection with factor analysis, all of the information was analyzed using SPSS and Smart PLS statistical software, and the KMO test was applied to examine the sufficiency of the questionnaire sampling. Cronbach's alpha statistic was used to assess reliability, and the value of the KMO test was 0.9, and it was good. These figures show research structural equation model for reported crash history. As I mentioned before, the final model contained 9 latent or exogenous variable, and we have one dependent endogenous variable, which is based on some assessed effective variables. A number give in parentheses represent t-value. All of t-value are more than 1.9, and the number shown on arrows are passive coefficient, also we call connection strengths. In general, we can say that positive coefficient, red color, indicate a direct association between latent and target variable, and negative coefficient, green color in the figure, indicate an inverse association. Often values greater than 0.7 for Cronbach's alpha and composite reliability indicate acceptable reliability, and also acceptance of the AV criterion typically requires a value greater than 0.5, and in this research, as shown in green table, all variable in current model poses an AV that is equal or surpasses a threshold of 0.5. The value of the main diagonal, which are greater than those of the lower triangular matrix, confirm the discriminant validity of the model. And using Pearson coefficient and the Fornell-Larker method, correlation between independent and dependent variable and divergent validity of the model were confirmed respectively. Also, in this table, according to these indicator values, this structural equation model has appropriate goodness of fit and desirable predictive power. This table shows correlation metrics between research variable according to the Pearson correlation coefficient, and also in this study, the variable of this questionnaire explained 8%, 32%, 18%, and 40% of the overall variation, respectively, all of them less than 50%. As a result, it is possible to assume that common method variance will not be concerned in this project. In terms of highlights, we can say that extroversion, neuroticism, psychoticism, and sensitivity to reward predict higher reported crash history, and introversion, demographic characteristic, behavior, sensitivity to punishment, and safety attitude towards safety predict lower reported crash history. Also, extroversion was the main influencing variable that had a direct association with the target variable of the model. For future study, an effective approach to bridging the gap between research and practical application involves assessing drivers' medical and behavioral cognitive abilities, as well as conducting psychological or psychotechnical evaluation. This can be achieved through the utilization of computer-based tests like electroencephalography or Vienna test system, and driving simulation. And about the limitation of our work, the reliance questionnaire developed elsewhere may have led to the exclusion of important data which could be determined with future qualitative and quantitative research. And also there is also possibility that self-reporting bias affected the responses to both the questionnaire and self-reported crash data. Also, this study was conducted just in the main city in Iran, Iran's provinces, between 31 provinces, so that generalizability of the result to all Iranian drivers can be established through replication studies in other provinces. And the last one, I'm grateful for the guidance and support of Drs. Hopkins and Dr. King, as well as especially my DA supervisor, Dr. Kockelman, for all of their help. Thank you very much.
Thank you, Ali. Yep. Any thoughts, comments, questions to Ali? And this is our last presentation. So feel free to ask as many questions as you like.
I'm at your service if anyone have question. Thanks.
Yeah, Ali, do you see the question in the chat box? Yeah, please go
Yes,
ahead.
Some psychological theory being that we can use in model choice, and we can gain some experience from psychological theory for this model choosing and work in transportation. For example, Gray theory, Ising theory, or Jung theory.
Okay, any other questions? In the meantime, I think this is the last presentation. So if there's no more question, I will hand it over to Jane Carlos and to introduce the next section, and that will start in about 20 minutes, the highlight presentation. Yep.
Thank you. I think that there is one
Mr.
question.
Yes, I think I see that too. Yeah, go ahead.
I mean, our extroverts more likely take the bus. We cannot talk about the take the bus or any, for example, cars. But in my research, I work on difference between different personality disposition and different personality trait, and their relationship with accident and crash. I think that most of research with personality work on crash proneness and accident proneness of different personality trait. But I think extroverts are crazier than introverts, and I think introverts maybe use public transportation than extroverts, maybe. I don't know.
Yeah, thank you, Paul. Thank you, Ali. Any other thoughts and comments, questions? Ali, it's pretty early at your time zone right now, right?
Thank you very much. I stop share. Okay.
Yeah, sure. So I think I don't see any more questions. So with that, I will close this section today, and thank you everyone for joining. But in the meantime, let me introduce Jack Carlos, and please, Carlos, can you take over the and introduce our next section? Thank you.
Much for joining.
Thanks. Thank you, Maya. Thank you, John Carlos, for Maya. I really enjoyed the presentation. I mean, the headliner speech. Thank you so much. Please stay tuned because we have more presentations in this session. But also in parallel, there is track 2. So we're going to continue actually with the first presentation, which is myself, and is about how our decision-making process impact our street crossing behavior, exploring the factors behind the use of desire lines. But also we have 4 other presentations. So just a bit of housekeeping. I myself try to stay present within 20 minutes or 15 minutes preferably, so that we can have time for all the presentations. So I just keep track of time, but please also remind me if I kind of pass my time. Okay, so here we go. So this is actually research that we did in collaboration with IMU-CRC and also the Victoria Department of Transport. And I acknowledge my co-authors and colleagues for this work, Maziar Yazdani, Associate Professor Taha Rashidi, and Dr. Alistair Fernell from the Victoria Department of Transport as our client. Basically, the aim of this research was to study the street crossing behaviors of pedestrians and to understand that what are the influential factors that people, when they're crossing the street, they take the shortest path, which is not necessarily the safest designated path. And we call that desire line. So desire line basically is defined as the most direct and the shortest walking route between modes of transport, like tram station and bus station across the road, but not necessarily the safest option. And where the provided safer route is longer and deviates from the desired line, then a proportion of pedestrians, individuals, they may not use it, electing instead to use the shortest route. So the objective, as I said, was identifying what could be the influential behaviors, the social demographic characteristics of people who inclined to deviate from the safe path, and also to provide some evidence-based design recommendations for the Victoria Department of Transport in Australia. The motivation was that basically there's a kind of knowledge gap in terms of the planning or upgrading the interchanges or the interchanges between multiple public transport stations. And we also are aware that there are clusters of serious pedestrian injuries at interchanges of public transport. And as I said, we did not have any statistic in terms of the numbers of those who use desire line versus the designated safe path. What are the individual factors? What are the environmental factors? If the weather, for instance, impacts these choices, or what are the route factors? For instance, what's the characteristics of the geometry design of the walkways or the crossing path at the intersections that make people to deviate from that, and also to understand the effectiveness of some control measures. And at the end, we wanted to kind of to examine what are some nudges that we can implement for safer street crossing behavior, although still that would be the next phase of this work. So in recent years, several studies have examined the pedestrian behaviors using shortest routes, but mainly they were concerned in the red traffic light crossing. These studies postulated that many factors may influence these choices, such as weather, congestion, individual characteristics, walking time, etc. So we conducted a systematic literature review, and then we categorized these influential factors into 5 main categories: the pedestrian-related factors such as gender, age, etc., and also traffic-related factors such as volume of the road traffic, the number of cars on the street, speed, and presence of on-street parking, etc., as well as the weather and time of day factors, For instance, if it's windy, sunny, cold, if it's during the peak hour or off-peak hour, and also the built environment factors, such as, for instance, the nearby land use types. Is there any cafe nearby? Is there any like the public transport facility, accessibility? How is that? So these were the factors that were found out in the literature to be significant. And then we picked two different intersections in Melbourne. One of them was Russell Street and Berkeley Street. And then you can see the red arrows, which represent the desired lines, whereas the blue arrows, they identify the designated safe path, which actually is longer than desired line. So we identified these arrows, and initially we wanted to do an image processing. We wanted to capture the videos or even with the drone or something, but then there was some issues in terms of the operating drones at the intersections, or even like recording the foot traffic of pedestrians. So what we did was basically we observed the behaviors, and we collected about 4,500 field observation during 1 week, 8 hours per day. So 2 hours of morning peak, 2 hours of noon, 2 hours of evening peak, and then 2 hours during late evening and night. And we observed, so basically the survey team, they observed the gender, the perceived gender, age, weather conditions, time of day, if there was any mobility impairment characteristics, and then also they recorded the number of safe versus desired line usage. And we tried actually to be more to take a very rigorous way to not bias towards the unsafe behaviors. Also, we did an intercept survey. That the intercept web-based survey was administered on a tablet, and it included questions about social demographic information, cultural backgrounds, even some information such as income that we could not really observe it in the field observation. And also we presented 14 hypothetical scenarios to people. And for instance, we asked that what would you choose, the safe path or unsafe path? In the previous, actually, the figure that I showed you here, we presented this figure, and then we asked them that which one would you choose most likely if, for instance, the weather is severe, or if, for instance, you were carrying a heavy bag or walking with a tram, etc. And then we recorded these things. So a big shout out to the survey team, including my PhD student, Kesewa Opoku, who actually managed the survey team. The method that we wanted to use, so for the field observation, basically we observed whether they used the safe path or desired line. So it was very simple binary logic model that we followed the very simple binary logic model. In terms of the ranking, the people, the respondents of online survey, the intercept survey, they presented during for those hypothetical scenarios. We adopted the multivariate ordered logic model and why multivariate? Because we actually wanted to jointly model all of these hypothetical scenarios together, because there was some kind of correlation per each individual answering these hypothetical scenarios. So again, that was a multivariate ordered logic model. I kind of tried to skip the boring part, and the joint probability actually was estimated as a full estimation matrix. And there was, so basically we included one extra term in the probability function of each indicator, the theta, which is kind of the agent effect to account for the serial correlation between the error terms. And these are some figures that I try to, I will actually explain, but these were basically observing the safe path versus the unsafe path, depending on each of these factors. So these are some results, like numerical results. Let me, just before jumping into that, for the hypothetical scenarios, there were 14 scenarios, as I said. We undertook a factor analysis to identify which questions exhibit comparable patterns of the behavior. So after trying different number of groupings, it was found that the grouping with two variables with two factors yielded resulted better findings. So this suggests that the variables can be simplified and represented by two main factors. The first one being named the impulsivity, and impulsivity factors confirm our prior hypothesis as well as the literature that, for instance, severe weather condition like windy or rainy, very cold, or being in a hurry, or for instance, poor line marking can make people to deviate from the safe path. And the other one was the risk aversion factors that, for instance, walking with a heavy bag or pram, that make people to avoid risky behaviors in a street crossing. So these are some numerical results that are kind of translated into this table that you can see. So basically, the field observation revealed that cold, windy weather, being male, and also avoiding crowd, and when people are in rush, their walking style is fast or running, then it means that they're most likely to use these lines, versus like in morning hours during peak hours particularly. And for senior citizens, those who are older than 65 years old or so, or if they're carrying a pram or a heavy bag, or they're walking with a small children, or they have a business attire, which could kind of imply that when people cannot really rush, or perhaps they're going to work, so they're quite familiar, they're commuters, they're quite familiar with the area, and also working with somebody else, or even interestingly, when they're using mobile phone when crossing the street, they rather to stick to the safe path, not the desired line. That was interesting. For the online survey also, we realized that, as you can see, for instance, when there's no traffic on the street, then they may use the desired line, versus, for instance, if they perceive that there will be a CCTV camera or a police officer, or if the safe path is attractive, then they may stick to it. So there were also some differences across two sites, and that was one intention that we did this trial in two sites to see that if there was any differences across these as well. And the thing was, one of the sites, as you can see, the crown side, at the end actually doesn't have a zebra pedestrian crossing. So this design layout enforced people to walk across the length of the platform to be able to cross the intersection. So they were more inclined to use desired line and to deviate from the safe path. So the design layout also was found more influential, as well as the low foot and vehicular traffic at that site. So there were a couple of design implications that we found out, and we actually put it forward. So implementing measures such as pedestrian friendly crossing, improving the accessibility of public transport, enhancing the safety of walking and cycling path definitely are necessary. And for instance, we suggested that installing passenger counters, because the presence of passenger countdown was one of the hypothetical scenarios, that people said when they know that how long they have to wait to be able to cross the street, then they're most likely to wait. So installing passenger counters at the tram, bus stores or stations also kind of we can understand that what are the transfer rate, the volume of both vehicles and pedestrians. We suggested that for the signal optimization guidelines, it's better to also prioritize pedestrians right now. All of these guidelines are written based on optimizing the vehicles, reducing traffic signal cycle to lower the waiting time for the passengers, designing two optimum scenarios of signal timing at the intersections, one without public transport, arrival or departure, and one with that. So with the sensors, once actually the sensors detect the public transport arrival at the intersection, then they can trigger another traffic signal. Otherwise, then to basically lower the waiting time of the pedestrian and consequently reduce the risk behaviors. Vehicle to infrastructure equipment such as DSR, CO, 5G communications also could trigger the PT signal timing. Installing pedestrian signal countdown, that are actually mistakenly mentioned it in the beginning. The other recommendations actually involve a coordinated and integrated PT system. Traditionally, the bus scheduling task is undertaken in the isolation of adjacent PT services. So it's just based on the bus route itself, but when you take into account the volume of the transfer between different routes, then it will help. Looking at the travel patterns, when you see that there are a high number of transfers between two public transport services nearby, then you can kind of detect that, okay, perhaps there are so many people getting off from tram station and then going to the bus station. So it's perhaps better to kind of design or shortening the distance between the stations, allocating proper time interval for passengers so that they can transfer without being in rush and deviating from the safe path, optimizing the schedule of the integrated PT system rather than the individual services, and even using some information VMS, variable message signs, to inform the next public transport service so that people can plan for it. There are also some design implications and interventions. So I'm also mindful of time. As I said, avoiding crowd was one of the items that actually was found to be influential in people using desire lines. So widening footpath and crosswalks, making them more attractive, using some very high visibility signs like or design layouts that you can see here. Provisioning central refuge, etc. So these are some of the recommendations. Educational campaigns, like community education campaigns. There could be some fun and creative social media campaigns for this. Organizing safety talks, safety walks and campaigns for the students as well. And developing some virtual reality simulations that demonstrate the dangers of using unsafe path. And also, again, involving community members in the planning process to kind of foster that sense of ownership and responsibility. And as I said, the presence of CCTV cameras also found to be important in making people to behave more safely. So even some fake cameras could be useful, some random police officer presence, and as I said, maintaining clean and well-groomed walking things. And then also there was one question in terms of the driverless vehicle, and there was a dichotomy in responses. So some people felt more safe in the presence of AVs versus some other people felt a bit unsafe. So but in overall, actually people we found that there is not enough public trust in AVs. So raising some public awareness regarding the safety of cabs through perhaps running more trials, installing 5G, I2B communication technologies, and informing people about that could be useful. And there were some potential future works, developing even a simulation-based model. For instance, in AIMSAN, it can be incorporated because these unsafe behaviors, none of simulation softwares now have this embedded in their platform, so it can be embedded, and using some nudge designs and behavioral experiments to evaluate the effectiveness of various design ideas. And again, designing some risk workshops, reviews, etc., so that the audit of different sites. So sorry for a very big rush, and so I made it 20 minutes. So basically that was it. Let's see if there is any question. Okay, so no question in the chat box? No, okay. So well, I'm the chair, so I cannot also ask myself a question. If there's no more question, then let's go to the next presentation by Xuan He. Xuan will talk us through her paper using open data and deep learning to explore walkability in Shenzhen, China. Xuan is a PhD candidate at the Department of Geography and Resource Management at the Chinese University of Hong Kong. Her research interests are transport geography, planning, travel behavior, and Xuan, over to you. You can start sharing your screen.
Okay. So I share my screen now. Okay.
Yes, so I stop sharing. You should be co-host, so you can see this. Yes. Yeah, we can see your slides. Thank you.
Can you see my slide?
Yes, go ahead.
Okay, thank you. Dear professors and friends, good afternoon. I'm Xuan He. I'm a PhD candidate at the Department of Geography and Resource Management at the Chinese University of Hong Kong, and my supervisor is Professor He Sylvia. It's my great honor to share our research here. The research topic is using open data and deep learning to explore walkability in Shenzhen, China. And this research has been published in Transportation Research Part B. Very welcome to cite and read our research. Okay, so now let's start with the research background. We can see there are two pictures here. These two pictures show different streets. And I would like to ask a question, which street would you prefer to walk along? And I believe most of us would prefer walk along the right street because the street on the right has abundant street greenery, it has sidewalk and the street lights. However, the street on the left has no trees, no sidewalk, and no street light. Obviously, the big environment on the right street is more friendly to the pedestrian. And walkability is this kind of concept is defined as a measure of how the built environment is pedestrian friendly. Walkability and walking have received more and more attention in recent years because walking has substantial benefits to people's health, including physical health and mental health. And also, walking can reduce the carbon emissions. Is beneficial to our environment. And a walkable city can provide people with better places to live and promote the healthy city development. After systematically reviewing the relevant literature, we identified several research gaps. The first one is about the walkability frameworks. Most previous studies utilized typical walkability frameworks like 3D or 5D frameworks. However, these frameworks developed from the perspective of urban farm and based on radar utility theories. They assume the pedestrians make decisions based on the maximum utility, the shorter time or shorter distance. But in reality, pedestrians may not perceive more walkable with the routes or areas with high utility. the shorter time or shorter distance, they are more willing to work on the area of routes. They're a safer or more attractive areas of routes. Obviously, this typical framework overlooks some important pedestrian needs. Also, they mostly consist of meso-scale built environment features at neighborhood level, and they use variables like land use mix, street connectivity, etc. And they overlook some micro-scale built environment features at street levels, like trees, street lights, and sidewalks and flowers. And this kind of street features reported have a greater association with working activity that the meso-scale ones. And the third gap is about data and the master. Deep learning can extract these micro-scale features from the open data like 3D images. And 3D images is a reliable tool to visually audit the built environment. It can save more than 90% of time and 94% of cost compared to field survey or field observation. But very few walkability studies utilize these promising resources. So we raised our research question, how to measure walkability from pedestrian needs by using open data and deep learning. Then the second part is methods. Our study area is Shenzhen. Shenzhen is one of the most developed large cities in China, and it has undergoing a fast urbanization in recent decades. Shenzhen also a pioneer city. The study of Shenzhen may inspire other Chinese cities. And by the way, we found that most of previous walkability studies have conducted in developed countries, the Western countries, and in some car-orientated cities, for example, the European countries or the United States, and very few efforts in developing countries. But in reality, walking is a primary transport mode in the megacity of developing countries. For example, walking accounts for more than 48% of daily trips of the residents in Beijing, also a large cities in China. And also walking accounts for more than 40% of daily trips of Shenzhen citizens. So our study of Shenzhen might enrich or add some evidence from the developing countries. And our study unit, the neighbor scale is 1 kilometer grade because it matched the concept of the 15 minutes walking distance neighborhood proposed by the Chinese government. And also the literature report that this unit performed well in observing built environment. And based on the social psychological series, we built our walkability frameworks from 4 pedestrian needs: safety, convenience, continuity, and attractiveness. There are also 4 main principles in the Chinese planning guidelines. And the frameworks integrate meso-scale and micro-scale built environment features. And these variables are extracted from diverse open data, including 3D images, social media data, Weibo data, and the POI data, current open data, and GSpace data. And the micro-scale features are street features extracted from 3D images. This figure shows how to extract the target street features from the 3D images. And first, we generated the sampling points along the Shenzhen road network. And then we download the Baidu 3D images in 4 directions at each point. And we totally collected more than 312,000  3D images in Shenzhen. And it covers more than 86% of the Shenzhen road network. And then we use deep learning semantic segmentation method to extract the street features from these images. And here is an example. The pixel with different colors represent different street features. The blue area represents sky. The green area represents street greenery. And here the red area represents pedestrians. And we test 16 models for each target features. And based on the performance, we choose 3 semantic segmentation model to extract the target 3 features because these three models has highest occurrence rate. And we trained them on the two open data sets, the Seascapes and 8020K. And we calculate the walkability scores and subdimension scores by using the information entropy weighting. This method is frequently adopted in walkability studies, and it can overcome the subjectivities of weight from artificial effects, and it can avoid information overlap between multiple variables. And then is the results. And the scores are divided into 4 levels, and the red colors represents the highest level, and the gray colors represent the lowest level. So these figures show the walkability scores in Shenzhen, and we can see is heterogeneous distribution. And we found that the areas with high walkability scores are clustered in urban areas and suburban CBD areas. And we found that the average walkability scores in urban areas is higher than the average scores in suburban areas. In terms of the 4 subdimensions, safety, for the safety, the CBD areas of each district have higher walkability, higher safety scores. However, the Yantian and Dapeng, the southeast part of the cities, has low safety scores. For convenience, areas with high convenience are clustered in urban areas and suburban CBD areas. And the Morris Eyes Index is really high and indicate that the working convenience is spatially clustered. And the third one, the continuity, the areas with high continuity are clustered in Yantian, Dapeng, and Luohu, and closer to the areas where the street view images is not available. And the last one is attractiveness, and we found an interesting phenomenon. The areas with high attractiveness are mainly clustered in the southern part of Shenzhen, close to the sea. And here is this sea. And also the Morris Eyes Index show that walking attractiveness is also spatially clustered. And based on the finding, we conducted the discussion and conclusion. And first, we found that the spatial distribution of walkability in Shenzhen shows the rapid urbanization in megacities of developed countries may lead to distinct profiles between urban areas and suburban areas. And we found that urban area is more walkable than suburban areas. That may be because the urban areas has higher population density and the more commercial and economy activities. So the urban areas may receive more government support and resources. And second, we found that in several decades ago, the urban planning in Shenzhen has a tendency to marginalize the backward active transportation, cycling, and walking, and they remove or narrow the sidewalk or bicycle lanes to widen the traffic lanes. And this car-oriented planning forced the pedestrian like this boy work super carefully on the traffic lanes or endangers the cyclists riding there without bicycle lanes. And these two photos are taken during my field trip last month. And actually, the government has realized this issue and made some preliminary efforts to improve the walkability in the cities. For example, in the latest planning in Shenzhen, they emphasized the priority to improve the walking infrastructure or provide a safer and more friendly environment for the pedestrians. And we suggest that the cross-sectoral collaboration towards the common goal of improving walkability is also necessary. And you know, the top-down policies in mainland China may easily overlook some pedestrian needs or mute some citizens' voice. So we also suggest that the bottom-up feedback and suggestions need to be collected, and the more citizens' voice should be heard during this process. In conclusion, our study proposed a novel workability framework based on social psychological theories and utilize open data and deep learning to explore workability in Shenzhen from 4 pedestrian needs. And our result shows that workability in Shenzhen is spatially heterogeneous, and the areas with high workability scores are mainly in urban areas and suburban CBDs. However, the less workable areas are mainly in the suburbs. And our findings uncovered the limitation of the built environment of walking, and also provide some policy indications and some preliminary built environment intervention strategies to the stakeholders and planners. And also it revels that in the rapid urbanization of megacities, walking as a basic transport mode tends to lose its priority, and we suggest more planning efforts should be made focused on improving workability in this context. And here's the reference. Thank you very much for listening.
Thank you so much, Xuan. Well, actually, I was texting you, and then I realized that I was in a wrong thing. So let's see if there is any question. So Gabriel thanked. Xuan, actually, my colleague, Associate Professor Mian Saberi, he has a startup venture here in University of New South Wales, Footpath AI. Let me just text it here. Now check that out, because that's actually what also he's trying to do. So I was just wondering that how did you collect data? Was it just image? Was it by robot, or was it LiDAR?
And actually, we use several open data source in our studies. For example, the 3-wheel images, and both of and all of them are open data, so it's open source data. And for the 3-wheel images, we use Baidu's 3-wheel images because Google service is not available in mainland China, and and we can and the 3-wheel images is open source, and the social media data we use the Weibo data because the Xingnan Weibo is the largest social media platform in mainland China. And then is the POI data. The POI data also from Baidu Maps. And then is the open, government open data is from the Shenzhen Open Data Portal. And I believe most cities, most of the largest city has their open data portals. I'm not sure, but I think most of them have their open data portal. And then is the GSpace data also from the online maps and use GIS to calculate some indicators.
Yes, got it.
Thank you for the question.
Thank you so much. Let's see if there's any question in the chat box. I cannot see that, but yeah, so actually I typed Footpath AI there. Check that out. Because in our studio there, so when you're talking about walkability, we're talking about walkways. Right, and usually Google Map or Apple Map, they have the images of streets, but not necessarily the walkways. And what actually my colleague is trying to do is using robots. I can so if you click on that link Footpath AI, then you can see that he has a robot with a camera on top of it, and then it just actually it walks in walkways, and then get the image of different streets, etc. So as if it's just a pedestal.
Yeah, cool. Yeah, I will
so
check
yes,
this.
there could be actually one opportunity to collaborate.
Yes.
Awesome. Thank you so much.
Thank you. Okay, I stop sharing.
Yes. So I saw. So next presenter is Gabriel Oliveira. And Gabriel walk us through his research on exploring the temporal variability. Oh, it's just like, okay, of crash occurrence using crash classifiers and consensus. So Gabriel is a PhD student at the University of Melbourne, and his research interests include road safety, transportation equity, electric vehicles, relationships between urban mobility and quality of life. Gabriel, I think I saw your name there, so you can now share your screen and unmute yourself. Yeah, here we go. We have your video.
All right, can you hear me?
Yes, we can hear you as well. So I stop sharing so that we can.
So let
Thank you
me
so much.
second. So here we go.
Before Gabriel, before you start, Xuan, I think Kesavo also has a question in the chat box, so you can continue chatting and answering the question. Gabriel, over to you.
Okay, so my name is Gabriel. I'll be talking about exploring the temporal variability of crash occurrences using crash classifiers and consensus clustering. This is a study with Patricia and Andrea as a co-authors. I'm a PhD student at the University of Melbourne, and I will be starting then. So before starting, actually, I'll be covering a little bit of backgrounds, and of course, like what the objectives. I'll briefly cover the methodology and try to focus a little bit more on the results and discussion before concluding. So background motivation, crash occurrence. So we think about road safety, and it's a major problem worldwide. So roughly 1.5 million people died in 2016, and as many as 50 million got injured, and that has like massive costs from medical expenses to lost productive, and even worse, is leading to be the 5th world causing of death in a couple of years. So to give a bit of perspective how things are in Australia. So Australia, it's doing a little bit better. I mean, way better than a lot of places, but still there's a long way to go. So currently is ranked on the 10th position among 36 OECD nations. This in fatality per head. So trying to address this to improve road safety, the local government of Victoria launched a road safe strategy covering a time span of roughly 15 years to halve road deaths and reduce serious injuries by 2030, and even a bolder approach to eliminate deaths in our roads by 2050. When I'm talking about this bold, when we look about the numbers from the state of Victoria, we can see from the 1987 to 2021 that there is a reduction, which obviously is very good, but there's still a long way to go because we still need to reduce this roughly 200, 220, 230 deaths in our roads to zero, or the first goal is to halve, but then to zero. So in this context, one of like critical things or ongoing research that we need to improve is the statistical analysis of highway crash data, aiming to improve our understanding of where and when crashes are likely to occur. So in this context, the main objective of this study is to understand how the likelihood of crash occurrence varies across space and over time for the city of Melbourne. And being a little bit more precise, we aim to identify locations and periods with similar frequency of crash occurrences, and to evaluate the extent to which and how it varies within and between years at different temporal scales. So we're talking about monthly, daily, hourly, and why we're talking about different scales, because crashes, it's an sparse event, which we need sometimes to aggregate it most of the time to have enough sample size to analyze it. So with that in mind, I will briefly cover the methodology, which is divided in 5 steps. So the first step is data organization. So we need to represent urban locations, which we can do for very different ways. So we can talk about census tracts, traffic safety analysis zones, intersections, for instance. And we also need to define which temporal scale we want to investigate, or we're going to investigate the problem. So having defined that, then we will search for crash patterns, spatial temporal patterns of crash occurrences, which is this here, the second stage. And we call it signatures of crash occurrences. And for instance, we have several signatures. Each one in our study, we consider a year as an entity. So we have a signature for the first year, for instance, 2016, all the way up to 2019. So we have 14 signatures, and we want to analyze to understand how similar the patterns that we find in these years, how similar they are and how different they are. So with that, we can better understand the spatial patterns of crash occurrence and temporal as well. So we have the signatures, then we want to classify, which will go for the third step of that. We want to classify, put them in groups, as each group has years with similar patterns on that. And then after classifying, we still have difference within these groups. So we will identify for each group, which is the fourth step, a typical signature. We can understand that as an artificial year that better represent all the signatures within a group. And we do that for different scale, monthly, daily, and hourly. So within that, we can understand, we can diagnose what's going on over the time, the evolution of crash occurrences and where they're appearing and what time. It's one of the goals. And then after we got these results, we have we explore another possibility, which is the fifth step, which is using the signatures to predict, to address a transportation problem, a typical transportation problem, which is crash risk prediction. And the way that we do it, we combine the signatures of different temporal scales to obtain probability crash risk maps, which we use for predicting crash risk. And the way that we predict, so we have these maps, and we identify the map that best match unseen observations. For instance, let's get the last year, a few observations of January 2019, and we use that to find the best map, which we're going to use to describe the probability crash risk, for instance, February, and so on. So that's the overall. And before going to the results, I think that's nice to show a little bit, trying to describe visually what the signature means. So here we have figure 2, which the signature for the year of 2010 for the hourly case. So what do we observe from the early mornings? We have a small intensity of crash occurrence that starts to increase as the city, let's say, lighted up, and people start to moving. There's more people on the street. We have the morning peak, and then you start like reducing or increasing a little bit, all the way up to the afternoon peak, then start to reduce not only the intensity, but where they occur, or they're most likely to occur, and then all the way up to the nighttime. So this is the signature. So going on and moving a little bit towards the results, but first the data. As I mentioned, I have 14 years of data from 2006 to 2019, roughly 11.2K appearances within the city of Melbourne, which is roughly 37.7 square kilometers. This has an average of 800 crash occurrences per year with a standard deviation of 60. And how the data is distributed in time. So figure A shows the distribution by hour of the day. So we can see the morning peak, the afternoon peak, which follows a little bit of human patterns. It seems a little bit, it's very similar to traffic data. So we have figure B, which by day of the week, so we have like a decrease on weekends, and then I have by months, which here see a little bit of a decrease by winter time. So that's our data, that's what we're using. So then we need to, I'm going to cover, now I'm going to try to explain with more details the results, the discussion. So the first thing, as I mentioned before, we need to define what do we understand by locations. So in this case, we define traffic safety analysis zones as our urban locations. Each analysis zone is defined by a similar frequency of crash occurrences. And the way that we define it, we split the city of Melbourne in very small grids, roughly 1.5K, and then we aggregate that using a clustering approach to obtain these regions. And then we need to define what is the best scale, like how many regions would be appropriate. And for that, we use the FBF test, the Brown Forest Pipe test. So here, to explain it, we have the zone systems varying from 10 all the way up to 55 regions with their mean crash frequency and variance. And over here, we have the FBF test 1 and 2 and their significance alpha. So basically, when you look in bold, if you define a zone system with less than 25 regions, it is too big to capture the global features, the local features, I'm sorry, of crash occurrences. And as opposite, when you look to FBF2, if you define regions higher than, if you define a zone system with a large number of regions, that's too small to capture the global features. So in this sense, we have a range of optimal scale. And in this study, we opt to the upper bound, which is 40 traffic analysis zones. So we have 40 regions, 40 human locations. So with that, then we need to define our signatures to identify our crash patterns. We do that using 2 clustering techniques, and we compare them, and then we move with one. I'm going to explain why. So we use K-means and Ward's agglomerative to cluster what? We are clustering first crash occurrence, the intensity of crash occurrence in each geographic unit, in each location, the coordinates of this location based on its centroid, and the time of the event, which we consider as a circular variable to capture the periodicity. And what that means simply is that we consider February close to January and December instead of being closer to June. So to capture that, we need a circular variable. So in this case, we have 13 years of crash occurrences, 13 signatures, and then the way that we define the number of clusters for each signature, we want to have a cluster that is homogeneous as possible. So when we look here on figure 4a, we are showing that as we increase the number of clusters, we are the TV, it's the total width invariance is being minimized. So that's what we want to minimize that. And then we also want to maximize the similarity between clusters. Within that, we define for the hourly case 42 clusters. The signatures are defined by 42 clusters for the K-means, 35 and 25 for the daily and monthly cases. And for the agglomerative, it's 45, 32, and 24. So at this stage, the results of between these 2 clusters are very similar. So we opt to use one of that to find the groups to follow up with the results. So then we identify 13 signatures. Now we want to see which year that which year of crash pattern is similar to which. So we do that using the normalized mutual information, which is a measure that we can evaluate how similar 2 clustering results are. So based on that, and using the AnyCut, which is another clustering algorithm, we are able to put the signatures that are similar into groups by maximizing a quality function that basically show to us that we have homogeneity within our groups. So figure 4a is just illustrating the case, the normalized mutual information for the hourly case, as well as figure B. So if you look, we have for the year 2014, have the lowest normalized mutual information, which shows that it's indicators, better speaking, that it is also slightly different from the others. And then we have figure 4c, which shows that the quality functions improve greatly when we move to 1 up to 5. So at this point, we classify the signatures, years with crash patterns, into groups, and then that goes to the next step. We want to represent these groups by a single pattern to identify what is the common pattern that is inside each group. So for that, we utilize some consensus clustering techniques, which pretty much find an artificial year, I suppose we can say that, for each group. So here in table 4, we observe that applying that, some groups improve up to 5.5% in their homogeneity and scores, all the way up to 7% for the monthly case. And one thing to note, I've mentioned that we have 5 groups for the hourly, but I didn't mention for the other cases, which is 4 groups for the daily case and 3 groups for the monthly case. Okay, so we have that. So what we can gain, what we can understand, how can we answer our objectives? So based on that, we can understand, we can analyze the signatures, which represent all the patterns that have been that we've observed in 13 years of data. And to understand the signature here is showing up one of the 5 typical signatures for the hourly case. So we have the morning distributions with low crash intensity, and it's pretty much the spread around the city. Then the city starts to light up our way to the morning peak. There is a reduction, and then we start to increase again until the afternoon peak, and then start to reduce again on late night. So the main takeaway in this point, it is we have these typical signatures, and what we can learn from that. So basically, for each group, for each signature, they have some similarities among themselves and also some difference. So the main similarity for the hourly case is that this morning and afternoon peak, they show up in all hourly signatures, which a way of explaining that it does follow your mobility patterns, which pretty much people waking up, going to access opportunities in the city center, which is this usually darkest blue, and then on the afternoon returning to their homes after accessing opportunities such as leisure, name it, studying, and so on. They have also other similarities, which this reduction on late night and concentration around the CBD, which is where we have the most venues for entertainment as well. And also this sort of pattern, which is pretty much more scarce on late night. But they are different as well. And how they're different, one thing that I think it's pretty interesting, is that from the morning to the afternoon peak, in some signatures, there is an increase of crash occurrences, and for other cases, there are a decrease. In terms of the daily case, we have, for the 4 signatures, we have a very clear pattern, and this pattern is Monday and Tuesday, they are very similar to each other for all cases. Wednesday to Friday, they show very similar patterns, and so on, Saturday to Sunday. And one of the main difference, there is an increase and decrease of crash occurrence, as well as the location as they occur for weekends. And for the monthly, it's a little bit more fuzzy, but we have bi-monthly spatial patterns mostly, and they vary the most in comparison to the other cases. And to close up, the last step, so with that, we can gain knowledge, we can provide some information for policymakers, we can better understand the distribution of crash occurrence across space over time. And but we go further, we explore how can we use the signatures to address a traditional transportation problem, which is crash risk prediction. So for that, we combine the hourly, daily, and monthly signatures to obtain probability crash risk maps, which you call as crash profile. Then we identify the best one to describe a future an unseen year, and we are evaluating that using the mean hit rate, which is a metric for sparse events. So what we observe here in this table is for coverage level from 5 to 20%. Coverage level means here 5% of the areas of the urban locations are considered as a hotspot, and so on, up to 20. We have the metric for the mean hit rate for our case, for a baseline, which is the historic average, for difference in p-values. So we always observe a higher mean hit rate for our case. And what is more interesting is that as we increase the coverage level, the differences start to increase and becomes statistically significant different So to conclude, the spatial and temporal distribution of pressure currents for the city of Melbourne, they can be represented over 14 years. They can be represented by small set of patterns. This small set of patterns, they indicate the existence of a well-defined pressure profile, which paves the way to address a range of transportation problems. And the one that we explore here is pressure risk prediction. And lastly, but not the least, the likelihood of locations observing recurring pressure currents over time, it is directly related with human mobility patterns. As I mentioned in the early case, the movement, the increase of pressure currents on the CBD and surroundings, and then during the morning peak, and then during the afternoon peak as well, follow human mobility patterns. So that's all. Thank you very much. And I'm open for questions. Thank you.
Thank you so much, Gabriel. Maybe for research. Let's see. I don't see any question here in the chat box. Please feel free to ask your question, or if you want to ask it yourself, please just I can unmute you so you can raise your hand. So Gabriel, I had just one question. So all of the crashes were just injury crashes, right? Because the clustering that you did, it was not based on the severity of crashes.
No, we didn't use any attributes of crashes, even like the severity or being active or not. We were very interesting about trying to understand how much over this period they change it. And I didn't mention before, because there is a lot of literature showing that the factors, the determinants of, let's say, of severity, they change from year to year. But there is not many studies tackling how the distribution, where they occur changes.
Okay, I see. So, and also in terms of when you actually looked at the signature, you mentioned, because you just looked at the occurrence of crashes, right? So the intensity was basically the frequency of crashes.
Yes.
And then, well, one of the findings was, yeah, when there are more people going to CBD during, for instance, morning hour, then there will be more crashes. But how about if you kind of normalize, or if you just study or analyze the crash occurrence per travelers? Or did you have any information on the number of travelers to kind of normalize based on that?
No, we didn't cross like with actually remote mobility data. That's like a further step. That's we are just looking roughly only on crashes.
I see. Yeah, that in that case, then you could not really study per, for instance, 100 of usual or something. Okay, thank you.
Yeah, that's a very interesting question. Thank you very much.
Yeah, thanks, Gabriel. So very looking forward to seeing your next presentations on your PhD, and good luck with your PhD. I don't see any question here. So let's go to our next presenter, Jia Gao, and Jia is going to talk about the relationship between residential dissonance and changes in travel satisfaction, evidence from dual owner household in Japan. Jia, I can see your name here. Yes, so you started sharing a screen. You also have to unmute yourself. I can see your video. So just unmute yourself.
Yeah, okay. Can you hear me?
Yes.
Can you hear me?
Loud
Yeah,
and
okay. Okay, sorry, I missed to upload.
Can you also introduce yourself, Jia? Because I didn't have your bio.
Of course, yeah. Sorry, I missed to upload my personal profile, and I just made a slide here to briefly introduce myself. And my name is Jia Gao, and currently I'm an assistant professor in China at Cheng'an University. And previously, I worked at Nagoya University in Japan, and do the GSPS postdoctoral fellowship. And I obtained my PhD degree at Utrecht University in the Netherlands. And my PhD dissertation mainly focused on the active travel and the built environment. And for my research interest is mainly focused on the active travel and built environment, and also the travel behavior and the residential self-selection problem. And for today, I would like to show my study for the causal longitudinal relationship between residential dissonance and changes in child satisfaction, and the evidence from the Japan. When I did my postdoctorate there, we do the survey data, and the co-authors the Professor Yamamoto, Dr. Sato, and also Dr. Herbage. And for the Professor Yamamoto and Dr. Sato, they come from the Nagoya University and Dr. University. So for the introduction, for this study, the topic mainly focus on the residential dissonance and changes in child satisfaction. And for the residential dissonance, it's also a further study for the residential self-selection. And until now, the most studies on factors affecting child satisfaction focus on the child attributes. And also for the research, they suggest for the residential built environment may also related to the child satisfaction. So for this study, we connected these two to examine the relationship. And especially for the the individual daily trip, they are all most of the trip are the rounder trips that begin and end at home. And however, for this kind of relationship, the residential self-selection may have partially affected this result. And for example, the people may typically prefer to live in neighborhoods that meet their travel experience. However, if we do not take into account the residential self-selection, the estimated association may be biased. And this is also has been studied by the previous studies. And we do these studies like the further steps of the exam that maybe many people may do not live in their ideal neighborhood, or they may not to use their preferred travel mode. And then we would like to see the effects of the residential dissonance on their travel satisfaction. Especially from this study, we focused on the individual and the household perspective. So because in multiple person household, the people decide the residential location may need to know all the people's preference and also their working or the location and so on to decide their residential location choice. And from this point, the household may have many different types of residence because in reality, one household location may not can be satisfied for all the household members. So here, for instance, we included two types of residence. The first one is for the consonant. It means like those who actually living in the location which also meets their preferred facilities. It's like the ideal location. And also for the second one is for the dissonant, which means the people living in a residential location may not be their ideal, may not be in line with their ideal location. And based on this, the residential dissonance may differ, even also differ in among the couples within the household. Especially for the people, the individual residential dissonance, because maybe one of the household member, the household location will be the consonant, and for the other one may be the dissonance. And in addition to the household level residential dissonance and consonance, the individual level residential dissonance is also another factor that we may focus on in this study to see, to explain the differences in couples' travel satisfaction, despite although the couples may live in the same residential location, but they may have the difference. And the sports may have different, also have the different travel experience under the different residential preference. And this is from the personal perspective for the different, especially here, for the different residential preference. We specifically specify for like the accessibility, aesthetics, and also like safety dimensions to examine the effects from the individual perspective. And for example, for the women may value residential security more, and also in contrast, the men may typically prioritize to the car size and also something like the parking space. So among the dissonant residents, positively, we further classify into the two different residential dissonance. The one is like the positively dissonant resident, better perceived residential environment than their expectation. It means that we refer it to positively residential dissonance. And on the other hand, for the negatively residential dissonance, it refers to the people living in even worse than they expected. So it would be referred to the negative residential dissonance. However, the distinction between positive dissonance and the negative dissonance of the individual perspective on satisfaction within the household couples have been limited explored. And also, as the spatial period during my stay in Japan, so we collect the data is under the COVID-19 situation. And unlike many other countries, in Japan, there's no mandatory, is restricted mandatory or legal forced lockdowns. So during Japan's state of emergency declaration, the government may advise the people to limit their outdoor activities, but it's not like the mandatory. So giving such kind of software measures in Japan, we think it may be it's a unique case to examine the household level and the individual perspective of the residential dissonance and the consonance to what extent of this effect have an influence on changes in travel satisfaction before and during the pandemic. So for the research question of this study, the aim is to what extent do residential consonance and dissonance at the household and the individual levels explain changes in travel satisfaction, especially among the dual earner households in Japan. As for our data, for the dual earner household, it means like because we collect the data in couples. It means like the surveys in household level for both couples, the male and the female have to fill out the survey. So the case study area is in Nagoya metropolitan area. Here we can see the map, and this is the Nagoya city, the location in Japan. And the Nagoya is the fourth largest, not most populated city in Japan. And this is the specifically the study area. The large area is Nagoya City, and possibly the survey characteristics we have to catch up to capture the both couples. So we extend a little bit of our study area to also including the surrounding small cities around the Nagoya city. Is including the data was collected in 2021 October in Nagoya. Initially, we have 1,000 participants from 500 households completed the survey. And since the focus of this study, after data cleaning, the 540 participants from 220 dual income household was retained in this study. And for the dependent variables here, we use the changes in commuting travel satisfaction and also the changes in non-commuting travel satisfaction. The methodology here is that firstly, we use the principal component analysis to make the factor actual factor. I will later to elaborate it, and then also vehicle syntax to apply the possible gender difference between the spouses, between the couples. And also for the methodology regression model, we use the logistic regression model, but later examine the gender difference by using the similarly unrelated regression estimates to examine the gender difference. For the regression model, typically we use a statistical control approach. So we add the key variables one by one to examine if the residential dissonance and consonance have the influence of the changes in travel satisfaction. So in total, for each dependent variable, so here is for two, the commuting and non-commuting. For each, they have 4 models respectively. The model 1 only include the built environment and changes in travel mode frequency and social demographics. And for the model 2, is added in addition to model 1, is added the travel-related attitudes. And the third model additionally added the household level residential dissonance. And on the other hand, for the last model, we added the individual residential dissonance, which was after we removed the household level residential dissonance. So for the, as I mentioned before, we use the PCA, the principal analysis is here for the actual and ideal residential relocation. And this is the major key independent variables we measured in this study. So in our survey, it's a very comprehensive survey, have more than we used here. But for the residential location point, we measured the two times. It's first is to ask for their actual residential location, like the preference. from the accessibility, transport, car alternatives, aesthetics, safety, and the neighborhood socialization dimensions to measure the actual residential preference, and also we measure the ideal residential preference. It's also in this same dimensions, using the same questions to ask for the actual one is like the entirely true and not at all true in 4-point lecture skill. And for the ideal one, it's like to ask them to answer the strongly agree to strongly disagree to measure the ideal residential preference. And for this study, it's there to examine the effect from the hospital and the individual level. And on the one hand, for the hospital level, residential dissonance was measured as the absolute difference between the ideal and the actual the residential neighborhood score. It's like we use the after we use the PCE and we got the score for each of the dimension. But for the hospital one, we to get overall score, the residential neighborhood score, and in order to capture the residential dissonance or consonance, we calculate it by using the ideal one to minus the actual one. And each of the statement was computed separately and averaged to generate an overall score. And also for the overall score, in order to reduce the influence of outlier, and according to the previous studies for the residential consonants, we use the scale is like the minus 0.21 to the 0.21. Not just the absolutely the 0. Also, for the residential dissonance is beyond the hospital types was identified like the residential consonant household and residential dissonance household. And for the individual one, we specifically to measure each dimension of the individually for their residential dissonance consonants. As I just introduced, we introduced for the positively residential dissonance and negatively residential dissonance, and also the consonant. And for the result, and here is the statistical descriptive to show the general. We use the variables. And here is displays the changes in child satisfaction according to the changes in travel mode for commuting and non-commuting. And this one is for the commuting one. It's for the between the men and women. And here we can see for the different travel mode choice, the changes during the COVID-19 and also the normal situation to see if they increase using any of the specific travel mode or not, or decrease or increase or no change. And for this one is for the changes in non-commuting satisfaction for both genders, and also same for the according to the changes in different travel modes. And here is specifically to see the individually residential dissonance and consonance for each dimension, as I just mentioned, for the 4 dimensions for the male and female. And most of male most of the female compared to the men, they are all had the consonance and the positive dissonance, which means they are much better perceive their actual residential locations than initial expectation. As we have the each of the dependent variable have the 4 modes, so it's very large tables here, difficult to show in one tables. And this is for the changes in commuting, the result in changes in commuting travel satisfaction. And the first model, the first one is the full model of each dependent variables. This is the changes in non-commuting satisfaction. And here is the result. And first, for the regression model result, we got the first one, for men, the distance to the nearest train station was negatively associated with commuting satisfaction, and where in contrast, the population density was negatively associated with non-commuting travel satisfaction among the couples. Our analysis of the individual level residential dissonance showed that negative dissonance of car alternatives and accessibility was negatively associated with commuting travel satisfaction for female. And this study suggests the individual residential consonance and dissonance play a role in changes in commuting and non-commuting travel satisfaction during COVID-19 pandemic, especially for women. The findings of the study are expected to improve the people's subjective well-being by promote sustainable travel patterns and enable the travel satisfactory of the people. And the discussion for and conclusion of the study is first, our study is in line with the finding of DeVos, who found that the dissonance residents' preferred travel mode may not be optimally accessible in their actual neighborhood. As I also showed the figure before, it says most people are like positively dissonant of their current living neighborhood. And our study uncovered that more than half of the couples were dissonant residents, and about the a third of the couples had at least one partner with the residential dissonance. And on the other hand, as the individual level, the most residents had positive dissonance, and negative dissonance occurs the least often. It's like we just mentioned in the figure. And secondly, the gender difference and in residential dissonance among the couples are notable. Especially we found like for the model of change in commuting travel satisfaction, women are more sensitive to the accessibility of the residential location than male partners. And thirdly, active travel seems to be more enjoyable among women in Japan, especially for the non-commuting. And an increase in bus use was negatively related to means changes in commuting travel satisfaction. And in contrast, during the women with decreased subway use showed a higher likelihood of experience decreased non-commuting travel satisfaction. This is because in Nagoya, for the public transport system, the subway is very popular in Nagoya city and also even around the cities. And people may not often use the bus to go out. And finally, regarding for the policy, the urban planning and the policy aim to improve the travel convenience may positively affect women's travel satisfaction. And we suggest for the target subpopulation groups, such as working women in rural in the households, to need the further exploration and attention, especially in Japan, in Nagoya. And that's all. Thank you. And
thank you so much, Jia. Thank you so much. I don't see any question in the chat box. Jia, to be honest, I was kind of distracted when you presented the regression model. What was
it's fine. Yeah, sorry, I missed the time, forgot the time because for the first time to
So I have one question regarding that regression model. What was the dependent variable? I was distracted. Perhaps you have already explained.
The dependent variable for the first one is for the changes in commuting satisfaction, and the second one is the non-commuting travel satisfaction.
So it was
The
observed
changes
in Likert scale, right? Like for instance, 5 Likert scale.
Yes.
But I'm just wondering that how, so was it an ordered regression model, or did you the levels?
Yeah, for the first one we have actually for the whole study we have the two types of outcome variables. The first one is the travel satisfaction, because we have the survey to measure the people's daily travel satisfaction from commuting and non-commuting, and based on the period we collect the data, and we further add another question to capture the people's changes in travel satisfaction for commuting and non-commuting respectively, to see during the COVID-19 period whether you how about your for example, how about your travel satisfaction is like you increase their travel satisfaction or no change, or even decrease about your travel satisfaction. So this is the changes in travel satisfaction, how we measure it.
So changes of the Likert scale, right?
Yeah. For like the decrease, slight damage. Dramatically decrease, slightly decrease, no change, slightly increase, dramatically increased, like the 5 degrees.
I understand, but I'm just wondering, why didn't you model it as an ordered nature? Because it has an ordered nature, right? They're ordered, basically. They're not really continuous.
For the changes, it's like the decrease, no change, increase, and in like this order. I mean,
yeah. But if you just model it as a normal regression, it looks like that you have treated that variable as continuous, whereas it's not really continuous. It's more ordered. It's more categorical.
Yeah, because here it's not like the continuous variables as the beginning we designed the question.
Yeah, definitely. I think that
order.
The homoscedasticity assumption of the regression, which is for the continuous variable, but then so maybe some improvement for future.
Yeah. So this is still we got the reply from the journal, and we are working for the revised version. Version at the moment. For this study.
Great, thank you, Jia. I can see the next paper also your name is there, but so the next presentation is on the influence of life events on the attitude, behavior, relationship among household couples, a longitudinal study. And Shihang Zhang. Do we have Shihang Zhang? I could not really. Okay, we have
Hello.
you.
Hello.
Hi. So perhaps now you can share your screen, Shihang. So you are the last presenter. So I would appreciate if you can kind of wrap up 5 minutes. Just like, so we have basically 27 minutes. If you can wrap up.
Okay.
20.
Okay.
That would be fantastic.
Okay, can you see my PowerPoint?
Yes, you can go full screen, and yes, over to you.
Yeah, good afternoon, everyone. I'm Shihang Zhang from China University, and today I'm sharing with our research the influence of life events on attitude behavior. The work was done by me and Jiqian from China University the Professor Iwahan from TU Dortmund and Professor Yamamoto and from university. I will introduce the research from the introduction, data and master results, and discussion and conclusion. First is the introduction part. A lot of you have familiar with research about the relationship between built environment, travel attitude, and travel behavior. From beginning, we lot of research focus on how the built environment influence travel behavior and how the travel attitude influence travel behavior directly according to the theory of the planned behavior or indirectly through the built environment, such as the familiar residential self-selection problem. And also travel behavior could influence travel attitudes and much as the travel attitudes could influence travel behavior according to the theory of cognitive dissonance. Also, there are other theories such as the attitude behavior context theory, such as the ABC theory and the habit theory, which sees that the travel behavior and attitudes are similar from day to day, as they are people have this habitual behavior. The more influence, the more related theory, according to all research, is the habitual discontinuity theory, which says that the life events could act as a disruption of the daily habitual, and also provide as a window for the policy intervention to move in to change our travel behavior and attitudes to make them more environmental. So this is the theory part. Also, we have a lot of empirical evidence according of this. For example, for the travel behavior part, a lot of research have mentioned that the child birth and changing jobs, car acquisition and disposal, and residential relocation, they influence the travel behavior. And also the residential moves, the changing jobs, and the child birth could also influence the travel attitudes. For the young, for example, Occurrences 3 years ago, the research found that young adults tend to have a far more positive attitude toward car use after they experience such life events. Also, we have the empirical finding that the life events could influence the child behavior and attitudes differ by gender. For example, after childbirth, women are more likely than men to face challenges related to the juggling the employment and family escort. And with the dependent children, is associated with a higher level of car use in men than in women. But the current research are mostly done at the individual level. There are still research gaps as to extent to which the attitude and the behavior relationship is affected by the life events at the household couple level. Also, it remains unclear whether one's life events affect his partner, the child behavior and attitudes. So for this, for this study, we combine the mobility biograph approach and the habit discontinuity theory, and use a model called the Beers adjusted 3-step multi-group latent class transition model. I will explain this later. Okay, this is the data and the math part. For the data, we use Netherlands mobility panel. It's MPN wave 2 and wave 4. It's 2014, 2016. After data cleaning, we have a family sample of 1,122 individuals from 5,071 partner households. We focus on 4 travel modes. That's car, train, public transport. That's bus, tram, and metro. We call it BTM for the later, and cycling. For travel behavior and travel-related attitudes, these two are indicators we used to get the latent class. So they actually are the dependent variable. The travel behavior are measured by self-reporting module frequency. The original survey, there are 7 scale. We merged them into 5 scale. From 1 is never use either of these travel mode, and to 5 frequently use. That's 4 or more days per week. For the travel-related attitudes, there are 7 items asked in the survey, in the MPN survey. That's safety, comfort, flexible, relaxing, time saving, happiness, and prestige. But according to the previous research, the prestige cannot really measure the attitude towards either of the travel mode in the Netherlands. So we move the prestige using the 6 item, average them to get 1 overall attitudes toward each of the travel modes. The skill is 5 skill. From 1 is strongly disagree to either of the item, and to 5 strongly agree to that each of the travel mode is safety, comfortable, or flexible, etc. So the one strongly disagree is also the same meaning of strongly negative, and disagree is negative, neutral, positive, and strongly agree is also similar with strongly positive to each of the travel modes. So that's the dependent variable. For independent variable, we focus on the life events and other control variable. For life events, we have 3 personal life events. That's changing jobs, stop working, work more often at home. It's telework. And 3 household life events. Childbirth, car disposal, and residential move. As to the data limitation, the changed jobs is actually life events of a combination of 2 life events. It's get a new job and start working. And we didn't distinguish the residential move between you either move from urban to rural, or from rural to urban, or as from rural to rural or urban to urban. We didn't distinguish that because of data limitation. And for the control variable, we also have 3 individual variables: as age, education, and the job status, and the 3 household level characteristic, as gross household income, and dependent children less than 12 years old, and the urbanization level. And for the model, we use the LM model. It's a latent Markov model, also called latent class transition model, with covariance. It is I show the basic conception of this model. It's the latent class. It's composed of the latent class model across time. That is a latent Markov model. Latent class model is a classic method that, according to several indicators, to class individual into different clusters. And in this study, we use travel frequency and travel-related attitudes as the indicator to get our latent class. And we consider that how the latent class transition between the wave 2 to wave 3. That's between time from 2012 and 2004 and 2006. That's the latent Markov model or latent class transition model. And we also consider how life events and other variables influence the transition process. So we added the other variable, covariates. So we use a model, family is the LM model with covariance, also called the latent class transition model with covariance. Also for a different approach, basically there are 4 approaches. They call the one-step model, one-step approach, two-step approach, and classical only 3-step approach, and the best adjusted 3-step approach. As the one-step approach and the classical 3-step approach are best, so we use the best adjusted 3-step approach. It also could be done by 2-step approach, but we just choose the best adjusted 3-step. This is a model and estimation approach. This is another conceptual model to clarify some concepts. So that's the model is basically could be defined as 2 parts. One is a measurement model that we get the latent class. We call it attitude behavior patterns from the 2 indicators, travel mode frequency and travel mode attitudes. Yeah, these 2. And a structure model to modeling how other variables, the control variable, or we focused on the life events, how they influence the latent class and how they transition from different class across time. And another problem with such research is that you have to make sure the measurement invariance between different time, because this is time 1 latent class we get based on the time 1 travel indicator. This is time 2 latent class we get based on the indicator from the time 2. So we must to make sure that the different class, the class measured from time 1 and time 2, they are the same latent class. This is the measurement invariance. Invariance called they are the same. So we can compare them and to know how they changed from time 1 to time 2. So for the measurement invariance test, we use a method called the multi-group latent class model. The more information could refer to Congress 2018. Okay. That's the result part. And firstly is how the latent variable, how the indicator of the latent variable distribution. So this is for the car trial mode frequency and trial mode attitudes. And we can see that for mostly individual, as for man and woman, they use regularly or frequently of the car, at least once per week. And they have positive or strongly positive attitude toward the car also. Also, the men are more likely than women using car frequently and have more positive attitude toward the car than women. It's similar for 2014 and 2016. This is the trend trial mode frequency and trial mode attitudes. Most individuals never use train or occasionally use train. Mention is less than once a month, and they have neutral or positive attitude toward the train. For the bus, tram, and metro, BTR, most men and women also never or occasionally use them, but they have neutral and disagree or neutral and negative attitudes toward the public transport. This is the difference between BTM and the train. For the train, it's a neutral and positive mostly. And for cycling, most men and women using cycling regularly or frequently, and they have a more positive attitude for the cycling. We have cluster men and women or other individual based on travel frequency and attitude. This is a figure that generally shows how the latent classification based on the travel frequency and the travel attitudes. This one is for the car, and there are slightly different between men and women. You can see that men with strongly positive attitude toward the car and sometimes using car is clustered as cluster 1, the red color, but this part of woman is clustered as cluster 2, is a blue color. And this is for the train frequency and attitude classification, and this is the BTM classification, and this is the cycling classification. There are also a slightly different for the cycling classification between men and women. Here you can see, and the bar here is how the different cluster distribution. For the cluster 1, for the car cluster 1 is car lover. We will explain it later, and we named the different cluster as 1, 2, 3. For the 1 is the most individual cluster, dominant cluster. It's but this is we didn't show the difference of men and women distribution here. This is the overall distribution in the bar. The more detailed information could be seen as okay here. This is the profile of the 2 cluster latent class model based on the pole sample, and this is of all individual for the individual. This is a male, and this is for the female. They have cluster 1 and cluster 2. By the way, we also conduct the measurement environment invariance for the different gender. That's for male and female. So the meaning of cluster 1 of male is the same of the meaning of cluster 1 of female. So we can compare of the cluster 1 of male and cluster 1 of female. By this distribution, we call the cluster 1 as car lover because they use the car regularly and frequently, most of them in cluster 1, and have a strongly or positive or strongly positive attitude toward the car. And for cluster 2, most of them use the car sometimes or occasionally. There's nearly 75% and for male and 68% for female. And the attitudes are mostly positive or neutral. So we call the second class as car dispensal. As for the train, we get 3 cluster latent class. For the first class, we can see that most of them use train only occasionally and have neutral attitude toward train. And some of them never use the train, but they have attitude or strongly attitude toward train. So we call the class 1 as train potential. For class 2, most of them use the train at least sometimes, and have most of have the positive attitude toward the train.
I'm so sorry for distracting you, but can you wrap it up in 1 minute? Thank you.
Oh, okay. And this is class 2. We call class 3 as non-train user, and never of them use the train. Similarly, we get the BTM captive, BTM enthusiastic acid, and the BTM hater, and the cycling enthusiastic second level and the cycling avoider. This is the latent class model. So we also get the latent transition model results as different life events, how they influence the transition between the cluster for male and female. This is the main result. I highlight some of that need to mention. That's working more often from home for male, and childbirth for male, and car change. That's car acquisition for male and female. That's they move from class 2 to class 1. That's and also residential move stimulate later individual from transition from class 2 to class 1. Okay, this car, and this is for train. Also, we can see the partner's life events could influence the individual's transition process, and the changing job could influence from class 3 as non-train user into train enthusiastic and train potential, and also childbirth influence them from class 3 to class 2 and class 1. This is the BTM. That's also we have seen the changing job move them from class 3, that's BTM hatred, to BTM captive, and BTM captive. It's more bigger than for women than for men. Also childbirth and car acquisition. This is for the cycling. We can see the working more often from home and the residential move, and also that's partner working more often from home and childbirth having more influence for women than for men. Okay, this is a general conclusion. We found that men and women differ in terms of the child behavior, attitude pattern, and the transition between the pattern. And also, both personal and partner life events affect the transition between and the attitude pattern. Also, the life events on child pattern transition differ by gender. And also is that life events experienced by individuals could influence their partner travel behavior and attitudes. For the policy implication, and we can see that life events provide opportunity to establish neutral patterns, especially for changing jobs, residential and childbirth. So for changing jobs, we suggest that offering public transport coupon or subsidy to employees who have recently switching job and developing a custom-made public transport travel plan would be help them to move or transition more from the non-transport public transport user to public transport potential or captive user. We also have some limitation. As first is as to the data limitation. We did get to the more detail of some life events. For example, the limiting effect of car ownership, also how they moved from urban to rural or rural to urban. Also, we model the latent class for each travel mode separately. Future research could consider to invest them in one model simultaneously. Okay, that's all. Thank you. So, any question? Sorry, I can't hear you.
Oh, I was mute, sorry. So thank you so much, Shenzhen. We actually ran over time, but I don't see any question in the chat box. I have just one question for you, because from the result that you presented, you look at each individual level of the indicators separately. Usually when I don't know, at least for me, the latent models, when we model the latent variables with some indicators that have been observed in Likert scales, we basically model those Likert scales of indicators as one ordered probit model or ordered logit model. And then we model that instead of just looking at individual level of Likert scale. That was, to be honest, the first time that I was seeing the levels separately. We looked at different percentages in each level of the indicators. Why was it? Why was that the case?
I'm not sure I get you, but I think that the latent transition model is based on the patient model. Wait a moment. Okay. I'm still sharing the.
I cannot see anything.
Okay.
No.
Okay.
Okay. Yeah. Now you are sharing.
Yeah. The latent class model based on the indicator of travel mode frequency and travel mode attitudes. We get the latent different latent class for them, and this latent class 1, 2, or class 1, 2, 3. They are actually yes, they are actually use a multi-logit model in the latent. Yeah.
For the classes, it's okay.
It's actually a logit model. It's actually treated as a logit model in the latent transition model or the latent Markov model. Yes.
Yeah. So, but and my question is regarding the indicators. The indicators, for instance, is travel mode frequency, and it's in 5 level. How did you model the 5 level of indicators? For instance, the travel frequency.
This is also treated as a logit model to get the latent class, to get different latent class. Yes.
Yeah. Okay. Maybe I have to read your paper. Yeah. If your paper has been published, yeah, feel free to share it. Has it published? Have you published your paper? The paper, have you published it or?
You're in the process.
It's in the process. Okay.
It's a second review, under the second review.
Okay, awesome. So I don't see any question there. Is there any question from Shangjian? Otherwise, thank you so much, Shangjian, and also your co-authors.
Okay.
So with that, then I reckon that we can wrap up track 2 of day 1. So the Western session will start in 8 hours from now. It will be 1 a.m. in Sydney time. I'm hoping to stay awake, but there's no expectation for you guys if the time zone really doesn't match. So the Western session will start with a headliner speech by Professor K. Exhausen. K is very well known. He doesn't need an introduction. So if the time zone allows you to stay awake and watch his headline speech, please tune in. Otherwise, then we'll see you next day, tomorrow. So tomorrow there will be the headliner talk starting same time that we started today. Although the headliner actually started the session the day by Professor Khanpour from Monash University, and then we have a special session on connected autonomous vehicles, very interesting ones. We have invited some government managers and even and also researchers who have been heavily involved in some real world trials here in Australia. So, and then also there will be one special session by the National Transport Research Organization, NTRO, in the last 2 hours tomorrow. So please tune in. I bet that you will enjoy. So have a nice evening, afternoon, everyone, or morning, maybe your time. Hope to see you tomorrow. Thank you.